Looks like we're live. Hello everyone and welcome to yet another recreation programming session with Azuzin. Let's make a little bit of an announcement and officially start the stream as usual. Red circle live on Twitch, and not what we're doing today on Twitch at .television website. Today we are developing a new language in Rust for Erlang VM, and the reason we're doing that is because I want to. Right, that's literally the reason, because I want to. Don't ask me, Zazin, why are you developing the language? Because I want to. I can do that, and you cannot. That's why I'm doing that. That's why I'm doing that. To dab on you. So, right, I'm joking. So I'm gonna give the link to where we're doing all that, twitch.tv/studying, and I'm gonna ping everyone who's interested in being pinged. There we go. The stream has officially started. I'm not even sure if I'm gonna actually succeed today. So yeah. I'm being preemptively cocky, but that's fine. That's fine. So what we do on the yesterday stream? Not really yesterday's stream, but the previous stream, right? So we did a very simple thing. We created a simple program called Hello, right? So and then we compiled it into Beam, bytecode, and Beam, as you know, is a virtual machine for Erlang, right? So, and it's a simple binary file and stuff like that. So we took a pretty cool book, and I really recommend to check out the book. It's called the Beam book, right, and it's basically a book about internals of Erlang, right? And using that book, using some snippets from that book, we implemented a simple parser for the Beam file format, right? A simple parser for the Beam file format. And essentially we can even take a look at how it works, right? So here is a simple thing. We already compiled it, right? So that created the module hello. We can take a look at the module info of that module, right? So, and the most important thing that we can see in here is that it imports the function hello, which means that I can actually call this function and it will tell me hello world. There we go. The function seems to be working. So here is the parser, right? So off screen, I actually implemented parsing for the rest of the important chunks. I think I have not fetched it. So let me actually quickly fetch it. Right. So I'm going to merge that and open it up one more time. So let me revert the changes. So yeah, so essentially this parser parses all of the important chunks, right? As far as I know, there is like four or five important chunks. So it's the code chunks, which contains the bytecode, the instructions, the encoded instructions, the atom table. Atom table is basically a list of atoms which are symbols, which are just strings, right? It's a list of strings. Then the list of imports, the functions that your module is going to use, the list of exports, the functions that your module is exporting, and the list of string literals, right? So that's basically sort of like the main chunks that we're operating with, right? So these are the main chunks we're operating with. Right, so, and I can compile this entire thing. So it exports the function read, which allows you to read the Beam file, right? So we can do hello Beam. Right, and we can see the internals of these five chunks. Here are the atoms. Here is the code. We don't really parse the code instructions, right? The code, the instructions themselves are encoded in a very anal format. It's so freaking anal that I decided not to implement it myself, right? Right. So it's not really that anal, but it's a little bit anal. It's called compact term encoding, right? It's called compact term encoding, and essentially the arguments, right? They have a value, some sort of an integer value, and a tag associated with them, right? And the purpose of this encoding is to cram as much information as possible in the least space possible. Right. So, and essentially, if you have a value that is, I think, less than 16. If you have a value that less than 16, the tag and the associated value fit entirely into a single byte. A single byte will contain a tag and a value that is less than 16, because tag is stored in the first 3 bits of the bytes. Yes, that's how fucking anal it is. When I said that this format is anal, I meant it. It's a very anal format. Right, so, and if you have a value that is greater than 16, they use slightly different encoding method, right? So I think it's up to 2000 or something, up to 2000. After 2000, they use a different schema that expands the amount of bytes. So it's basically the arguments have a variable length and stuff like that. So the purpose of this entire shit is to preserve the amount of disk space. It is needed to preserve the amount of disk space. So when the loader loads up this instruction format, it actually expands each individual argument to be word aligned. So during the execution, it's not that slow, right? So it is needed to sort of like, you know, cram as much information as possible within like a small amount of space, because I suppose this code, maybe, this is my hypothesis by the way, I don't know for sure, but maybe this code is meant to be also transformed over the network, because it's a language for distributed systems and you can hot reload over the network. So maybe to save some space, save some traffic on that or something like that. I don't freaking know. This language is from 80s. I don't know the decision process of this kind of language, but it is what it is and it isn't what it isn't. Luckily, there is like already algorithm baked into Erlang that allows you to encode arguments in a certain way. They don't really expose the algorithm for decoding the arguments, but they expose the algorithm for encoding them. Right, if you go into the Erlang, there is a module called beam-asm. Right, so let's take a look at what it exports. Module info. So what does it have? It has quite a few. I think it doesn't have that much. Right, the most important thing it has is an encode. Right, so you can do beam-asm encode and you can provide the tag. You need to know the number of the tag, and the number of the tag is one of those. Right, so essentially literal is going to be 0, integer is going to be 1, atom is going to be 2, and so on and so forth. Right, so let's say we're going to actually encode something like literal, and we want to encode a number 2. So, and this is the thing that you've got. Right, and it's going to be a single byte up until, I think, 16. Right, after 16, like starting from 16 is going to be 2 bytes. Right, and I think after like 2000 is going to be like more than 2 bytes, and so on and so forth. So it's basically extends, right? So and you can use this kind of stuff. And there is also like a list of different tags that you can use for this kind of thing. I think it's all located near the beam-asm, right? So let's actually find out. So let me find file with the name beam-asm. Right, what do we have in here? Okay, here it is. So here's the beam-asm, and there's also a header, right? So if we take a look at this entire thing, OpCode, yeah, there we go. So there are OpCodes. Here are all of the tags. So there's 8 tags in here for different types of things. And right, there's also OpCodes for different instructions in here. Here are different instructions of the Erlang virtual machine. So this entire function tells you basically, given the name of the instruction and its arity, it gives you its opcode that is within the bytecode. Right, that is within the bytecode. There's also opname that does the opposite thing. Given the number, it gives you the name and the arity. Right, so yeah, that's basically the kind of stuff that we will need today. Right. So, and within the module, right, as I already said, we have atoms, we have code, we don't really have any strings, so we have imports and we have exports and so on and so forth. Okay, we can kind of parse the beam files. So today I would like to do an opposite thing. I want to generate a beam file from scratch that is loadable by Erlang virtual machine. I could do that in Erlang. Sure, I could do that in Erlang, and it's actually kind of convenient because, again, there is a such thing as beam-asm encode. So if I need to start encoding things, I can just use this function. But I think it's kind of unsatisfying. I feel like it's a little bit unsatisfying. I feel like the beam file has to be generated by something that is entirely not Erlang. So the sequence of bytes must be generated by something that is entirely not Erlang, and I decided to go with Rust, I guess. Rust sounds like a reasonable thing to use for this kind of stuff. Right, so the goal for today's stream is going to be to write a Rust program that generates a sequence of bytes that is going to be recognized by Erlang virtual machine as a legit Erlang module. Right. So, and maybe generate some functions that perform something and stuff like that. Right. If we manage to do that, I'm going to declare today's stream a success. Right. And once we have something like that, making a programming language out of that is going to be actually rather easy. Right. Basically implement like a Elixir, Parser, and just generate the final code based on that syntax, right, that you parsed and stuff like that. So yeah, so that's basically going to be the goal for today's stream. Write a Rust program that generates a Beam module. We already kind of know how Beam modules work. And if we manage to load it up and maybe even execute some functions out of that module, it's going to be a success for today's stream. Sounds good? Sounds Gucci? Sounds Tamaguchi? Let's go. So let's go ahead and create the file. So the language that I want to create, I'm going to call it Bada. You will know why a little bit later. You will know why a little bit later. So I'm going to do Bada RS, right? So, and let's first create, hello world. So this is going to be hello Bada, I guess, I don't know. And let's just compile that. Rust C, Bada RS, and there we go. Let's just wait a little bit. There we go. So we got hello world. How about that? How about that? No cargo. Why do you need cargo? Listen. We are generating a sequence of bytes from. We're just generating a sequence. We're just generating a sequence of bytes. I know in 2023, with the current software development standards, it sounds insane and it feels like you need to have like a very complicated framework to do that. But this is the capabilities that Rust has in a standard library. In a standard library, it has the capabilities to generate the bytes. I know it sounds insane, but trust me, it is possible. It is possible. Right. How can you generate a sequence of bytes? Right. First of all, you need a container for those bytes, right? So let's actually create something like bytes. Right. So this is going to be vector new, right? So, and let's say this is going to be vector of bytes. There we go. We have a container for bytes. So the next thing we want to do, we're going to just push some bytes into that container. 69. Let's actually do that 3 times. Why not? So, and if we open up the documentation for Rust, for the standard library, right? So let's actually take a look. There is a pretty cool package within the standard library. It's called write, fs write, right? So there we go. So what this thing does, it accepts the path and the contents, which is something that can be interpreted as a reference to a slice of bytes. So essentially, what I can do now, I can do fs write, and let's create for the name with the name for the file, right? So it's going to be Bada, and the extension is going to be Beam. That's exactly why I decided to call language Bada, right? So because the final file is going to be Bada Beam. Haha, very funny. Anyway, so and then you just provide the reference to this entire thing, and then you say expect. Maybe we're going to even extract this entire thing to file path. Right, so file path like this. So, and we say that we expect this specific operation to not fail. Right, I'm going to try to compile this one more time. Right, We have to import this specific thing, stdfs. Right, this entire thing has to be mutable because we're pushing it, we're mutating this entire thing. And there we go. It generated file Bada Beam. And if we open it, right, we hear this Bada Beam, and we open it in hex mode, it's 45, but it's in hex, right? If you convert hex right into decimal, right, so 45, it's 69, so it's basically 69 3 times, and all of that without any third-party dependencies, using only the standard library. I know it sounds insane, but Look how much shit you can do just using standard library without cargo, without overcomplicating thing, just vector and the right function. Repeat after me, just vector and right function. Oh, you want a framework? You don't need framework. You don't need traits. You don't need hierarchy. Just vector and right function. Repeat after me. Just vector and right function. It's that simple. You don't need anything else. You don't need to overcomplicate anything. Just vector and right function. Get it? Okay, cool. And that's how we're going to be generating. So with these tools, with these two things, just vector and right function, we will try to generate a file that is going to be recognized by Erlang as the module. Right. So that's going to be the goal for today's stream. That's going to be the goal for today's stream. Alrighty. So, how do we generate the thing? So right now, if I try to like even load this file with Erlang, it's not going to work. As far as I know, in Erlang there is a module code, right? So which is responsible for loading the beam files, right? So we could use compile, right? So usually we load things with compile, right? So C, and you have to provide specifically an Erlang file, right? But we don't have an Erlang file. We don't have an Erlang file, we already have a compiled module, just bytecode, right, that was generated not from Erlang file, but from scratch, literally. So for this kind of situation, I think there is a special function in the code module, right, so which is literally called load file, right. So, and it tries to load the Erlang module using the code path. It looks for the object file with an extension corresponding to the Erlang machine used, and so on and so forth. Okay, so let's actually try to do that. Code load file, right? So, and let's just load bada beam. Oh yeah, I think I remember. So you're not supposed to use the string. You're supposed to actually provide the atom without the extension. There we go, and we cannot load that because it says corrupt file. And here's an interesting thing: it crashes within the C code. Right, so the loader for the bytecode is actually implemented in C. Right, so, and we can even probably find the location where it was located and stuff like that and know exactly what's going on in there. All right, so if I do something like, maybe just like look for that. So is there, so there's Elixir forum, disgusting. I'm gonna go to Google. So there we go. So here is the GitHub. Thank you so much. And so we even know the line where this kind of stuff happened, right? So we even know the line. And so the line is 144. Is there any way to jump to the line? I think there's no way to jump to the line. Maybe Control L? Nah, it doesn't support that because it's freaking GitHub. Right, so there we go. Corrupt file header. Yeah, corrupt file header. So it literally failed in here. So what it does, right, it tries to read the code, right? So then you have a bunch of results, different errors, right? So these are different errors that may occur while loading the beam file, right? So we can just read that in here actually. Right. So right from the C code of the virtual machine, it's not even that you know, that unreadable. It's just C. It's a pretty straightforward C actually. Maybe we can modify that. Maybe we can use that code as a documentation on the format. Right, so maybe we can do that. But we'll see, So the first thing we need to do, we need to generate the header, right? So, and if I remember correctly, the header actually starts with a magical number 41. Right, or rather magical combination of characters. Then 32-bit size of the whole thing. I'm gonna sneeze. Right. So it's a size of the whole thing, excluding 41 and the size itself, and then the beam magical, you know, magical thing for the internal sort of format. Right, for the internal format. So as far as I know, 41 is a magical number for sort of like the container, and within the container you have another format which is beam, right? So I think they use like EFF files or something. That's what it is, right? Interchange file format. So this is what they use to store beam things. Right, so and yeah, within that thing they have beam. Right, so that's basically how it works. So okay, so we need to be able to push for one into the bytes, but as a sequence of bytes. Right, we need to be able to do that. So as far as I know, we can't really do that, so we can't really push this entire thing because it will push it as a single element in here, right? So let's actually remove this entire shit. So I'm going to try to compile that, and it is not going to work, right? So it's not how it works, unfortunately. So if I remember correctly, Vector implements a very interesting sort of like a trait called extend, right? So I saw this trait before, especially when I worked with Parser. Like a tree, you know, talking tree and talking streams and stuff like that, right? So I saw them relying very much on this specific trait, and it has an interesting method that is called extend, and it extends the container with an iterator, right? It extends the container with an iterator. As far as I know, Vector implements this specific method, right? So it just allows you to extend. So, which means, right, so we have a string slice, we can interpret it as bytes, and we can basically interpret it as an iterator, and we can extend, right, we can extend bytes with just that, which makes it rather easy to work with, I think, right? So let's actually try to do that one more time. Right, maybe, so there's also some sort of a mechanism in Rust that allows you to automatically convert slices to iterators. Maybe I can get rid of that. I can get rid of that. Okay, so we don't really need to do anything in here. Okay, so, and then if we take a look at the bada boom, okay. So yeah, there we go. So now we have 4-1. Now we have 4-1. So that's pretty cool. So the next thing we have to put in here, right? So the next thing we have to put in here, we need to put the size of the entire file, excluding the magic and the size itself. Right, so essentially we can just put 4 in there, right? So let's actually say 4, right, as u32. I think there was like a way to do it like that, right? I don't remember if this kind of thing works in Rust, but we'll see. And is there any way to convert u32 like to like big endian? Is there something like a okay? So I vaguely remember there was something like that, to big endian word, and it gives you an array, right? So, but then we can probably try to interpret it as a slice to big endian. Right, to big endian bytes, because Erlang uses big endian, right? Erlang uses big endian. So now what we can do, we can try to extend this entire thing. So this is going to be just 4. And then we probably want to do something like beam in here, right? So, and it's actually pretty straightforward, right? So we can just insert each individual element of the format, like with single calls extend, single call push, and stuff like that. I think that's pretty cool, right? And let's actually try to run this entire thing and open the bada beam, bada boom one more time. Bada beam, bada boom. Look at that. We've got a header of the beam file that easily. But is it going to load? Is the Erlang going to load this entire thing? Let's find out. Bada beam. So it does not complain about corrupt file header. Now it complains about missing code chunks. We just knocked off one goalpost. I'm sorry if it was too loud. So yeah. So essentially, this is actually very useful, by the way. This is actually very useful. We can implement the generator in series of goalposts, right? So essentially, first we just fixed the error of corrupt file header. Okay, next one, like missing code. Let's generate code chunks with empty code, right? So maybe then it will tell us something like missing that chunk. Let's generate that chunks, and another chunk until we just basically generated a minimal beam file, Right. So a minimum beam file. I think that's very interesting. Right. So this is a very cool approach. I really like developing stuff in this kind of approach, like interactive approach, because you can kind of see the progress. Right. You can kind of see the progress. I think it's really cool. So this is similarly to how, you know, quite often people develop emulators, right? So essentially they have some sort of like their favorite game, right? They implement like a stub for the emulator with a switch case for different opcodes that doesn't implement any opcodes. They try to run their game. It fails on a certain opcode. They implement that opcode, run it again. It complains about another opcode, and then they iteratively just implement the whole emulator. Right, or at least the emulator that can play their specific one game. But then you can try to implement it for another game, and eventually you will implement the whole emulator. So it's kind of similar to that. Right, so yeah. Bada bing, bada boom. So we need to generate the code chunk. What's the format of the code chunk? So let me see. So we probably need to find where refer to the code. Here it is. So yeah, they call it import chunk, which is rather weird. So it's supposed to be code chunk, but I copy pasted it from the book, right? So the book contains quite a few typos, right? So which is kind of funny, but anyway. So code chunk. I'm gonna copy paste it in here, I think. So this is not the comments that I expect in here. So how are we gonna be generating all of that? So I suppose maybe we're gonna have some sort of a function, right? So some sort of a function code chunk, which is going to accept opcodes, right? So, and I don't really know what's gonna be the opcode, right? So it's probably gonna be some sort of a separate stuff. Let's not accept any opcodes for now, right? Because I want to generate like an empty chunk, right? And see how it's going to go. So this entire thing is going to return, I suppose, the bytes of the chunks, right? So we're gonna just generate it as the chunks. And so let me see. So I'm gonna just say to do like so, and in here, I want to first pre-generate all of the chunks. So then later I can compute the final size of the file, right? The final size of the file. So essentially I can say plus code len as u32. Maybe it would even make sense to do something like so, right? So as u32 2 bytes. Right, and so now I don't have to worry about specific size of the code. If it's gonna get extended, that size is gonna be added to the final size of the file, and then we can say something like bytes extend code, right? Bytes extend code, right? And if we're gonna have even more chunks in here, something like atom chunks, right? So in here you're gonna have a bunch of atoms. Atoms are the strings, right? Not really strings, they're the symbols that are used within the module, right? So different names like hello, and that name then can be used for the name of the function. Some of the names can be used for the names of the modules that are imported or exported, right? So we can say like generate atom chunk for these specific atoms and stuff like that. So what's interesting is that some of the opcodes may refer to some atoms. So maybe we should be able to have like atoms as the table in here that we can reuse among several chunks, right? So because the way the code refers to the atoms, it refers to the atoms by index, right? So to refer by index, you need an array of atoms. Right, so we can generate the code from the atoms, so to know their indices, and then they generate atom chunks. So this kind of stuff can be reused in the future, but not for now. So I don't really want to overcomplicate this entire thing too much, right? So we're generating empty stuff. I'm jumping ahead of myself too much, right? Because as soon as you start implementing something interesting, it feels like you want to overcomplicate things, right? So build some sort of abstractions, build some sort of a framework, right? So build some sort of a framework. So let's not go there yet. And we don't even need the code chunk yet. Right, we don't even need the code chunk yet. So interestingly, what if we first generate the contents of the beam and only then generate the header or something. You know what I mean? Right, essentially, let's actually first generate something like this. So let's say we're gonna have a beam, which is the vector, right? And we extending the beam without caring about the size or anything like that. We might even inline the code in here, right? So we just generated the beam without the header, and then we have bytes. Here we do 5, and as the sort of size we say beam len, right? And then we extend the bytes with beam. That's actually pretty cool. So essentially then I can append more different chunks in here, like atom, so imports, right? So we have imports chunk, exports, and that will work automatically, right? That will essentially work automatically. So I think that's a pretty cool idea, right? So let me actually try to go to the compilation errors and see if it's going to work. So this thing has to be mutable. And now it complains about this specific part because the code is not implemented. Okay, cool. So maybe I can even use that paradigm for all of the chunks, because all of the chunks, they have this sort of thing where you need to specify the header of the chunk, the sort of name, and then the size of the chunk, basically the size of this section, excluding the name and the size. I can use a similar trick that I did in here. First, generate this part, and then once you have this part generated, generate this part. So yeah, this is actually like probably something that is going to work really well for sort of this kind of format, if you know what I mean. Right. So when a subsize is a very anal thing, right? It's the size after which the code starts. Right? This is a really weird thing. So the code starts in here, right? The code starts in here. So subsize, it's the size of this section. Why the fuck do you need that? Why the fuck do you need that? Here's an interesting thing. You may generate beam modules that have a bigger section than some of the loaders expect. So essentially, if you have a version of the compiler that adds additional fields in here, right, so some additional fields like full, bar, and so on and so forth, this thing allows all the loaders, all the virtual machines to skip this section and go straight into the code. So it is needed for backward compatibility. Right, so the newer modules with the newer stuff can be still loaded by older virtual machine, because these sort of things like helps them to know what they're interested in. So you can still preserve old fields in here, and the older loaders, older virtual machine will be able to extract information out of that, but then they're gonna ignore the newer stuff. This is actually quite clever. This is actually quite a clever trick, and I really like that. Maybe I'm gonna steal that trick in the future, right? So, and there is a lot of things like that throughout the Erlang virtual machine, actually. There's a lot of things like that, just sort of like a provisions for the future in case something may change. And some of them are really cool, actually. I really like that. So, yesu. So here's an interesting thing. We can take a look at what you're supposed to even have in here, right? So what you're supposed to even have in here. So opcode max is the maximum value of the opcode, right? Because of the opcodes, right? As you can see, their indices, they're growing up, right? So the first index is 1, 2, 3, and every time you introduce a new instruction, they just increment this specific opcode number, right? So by providing the maximum opcode number, you sort of declare what's the instruction set you're using, right? It's the instruction set you're using. And label count is basically the amount of labels you have within the code section. Labels is something that you can jump to, and the function count is the amount of function you have within the code. Nothing particularly special in here. So let's actually see. I want to take my hello module in here, and see the values of these parameters in there, so I can just put them in here and don't guess or anything like that. Right, so let me take a look at this kind of stuff. So there's a code. Okay, so the code just basically ignores the info section, right? So as you can see, we take the sub size, then we just take info and we completely ignore it. I think instead of ignoring it, we could have actually put it in here, right? So let's actually put it like this. So here is the info. Let me reload this entire thing, and I'm gonna basically do the file hello beam. The file hello beam. So here is the code, here is the bytecode that we got, and here is the info, but info is not particularly parsed. The info is not particularly parsed. Let's actually parse it properly. Let me take all of these things. And replace the info with, right? So this is basically what we need to have in here, right? So the instruction set, some other things, blah blah blah, right? So this is the things, right? So before we were actually parsing it as a chunk, now we're separating it, so we're extracting specific instruction sets, opcode max, label count, function count, and so on and so forth. Right, so now we can say that info is going to be just associative array of those things, right? So can we just basically take this entire stuff? There we go. And can I maybe shave off all of these things? I don't think they are particularly needed. For some reason it didn't want to put the semicolon in here, so I'm gonna just I wanted to actually turn it into a snack case. I don't think I will be able to do that in bulk, so I'm gonna do that manually like so. Alright, so I'm trying to construct an associative array. An associative array in Erlang is basically a list of tuples, right? A list of tuples, and each tuple is just a pair. First element is the key and the second element is the value. So and in my case the key is going to be just an atom that describes the name of a particular field that I'm interested in. So and here we have instruction set, opcode max, label count, and function count. So on top of that, I would like to maybe have the sub size as well, just to see what usually you put in the modules, right? So I would expect it to be something like 16, because this is 4 bytes, this is 4 bytes, this is 4 bytes, this is 4 bytes, like 4 by 4 is 16, so this is what I expect in there, right? But I want to be 100% sure, right? So here we go, here is the sub size, and I go here, we have the thing that extracts all of that information. So if I try to run this entire stuff, so that's the data we have. Okay, so for the hello module, right, for this hello module that we compiled from Erlang, right, the values for all of these parameters for the code section, are the following. Where is it? I can't find it. So the sub size is 16 as I predicted. Instruction set is 0. So if I remember correctly, they basically set the instruction set to like one version and they never changed it since they invented it. So that's why for the longest time instruction set was 0, right? And it's kind of funny, right? So I suppose you need to increment the instruction set exactly. You need to increment the instruction set number if you made backward incompatible changes. For backward compatible changes, what you can do, you can just increment the opcode max, right? So because if you're just adding new instructions, it doesn't mean that you cannot work with all the code. All the code that is going to work with newer virtual machines anyway, right? So because it just doesn't use the new instructions. The only way you need to do that, you know, increment this particular thing is when you have backward incompatible changes. So I suppose so far they had no backward incompatible changes. And to be fair, when you're developing a virtual machine, it's actually super easy to just append more and more instructions and just preserve the old instructions for backward compatibility, right? So quite rarely you need to change like literally everything, quite rarely. And that's kind of demonstrates that, I think, maybe. So it's like, it's similar to x86-64, right? So as far as I know, the modern x86-64 processors, they still can run MS-DOS. Can they? Can't they? I think they can. Like you can literally take the old MS-DOS, like from the floppy disk, and run it on a modern x86 64 processor, sort of. Like, but anyway, so all of the like majority of the modes and the instructions that are needed to run this old software, they're still kind of work there. Yeah, people say in theory, right? So maybe in practice it could be a little bit more difficult, but theoretically. So, but what I'm trying to say is that you can kind of go very long without introducing backward incompatible stuff. So you can go for relatively long. So that's probably why the instruction set is just 0. So label count is just the amount of labels, and the function count is the amount of functions and stuff like that. You can actually see labels if you use a disassembler. Erlang comes with its own disassembler, right? So there is a beam disasm, right? So let's actually take a look at the module info, right? So beam disasm. And you can disassemble a particular file, right? So you can disassemble a particular file. So let's take a look at hello beam, right? And there you go. Here are all of the functions. Here are all of the functions that you may have. And within those functions, you have labels, right? Different labels, so we can even search for them, right? So these are different labels. And those labels are basically the places where you can jump to during the execution, right? So these are the labels, and so that particular thing, right, label count, it tells you how many labels you have within the code section, right, and the function count is how many functions you have within the code section. You can actually kind of see them. Each individual function actually starts with func and fo, right? So func and fo denotes the beginning of the function, right? So, and I suppose, I don't remember, you have to have like a label right before func and fo, right? And then label right before the beginning of the body of the function or something like that. So this kind of sequence of things like label, func and fo, and another label is sort of like a preamble for a function, right? And when you call a particular function, the execution jumps in here, right? The execution jumps in here. So when the func and fo tells you the name of the function, right, actually, yeah, so the name of the function and the some module info. I don't really know what the fuck is that. Oh, it's this one. Yeah, there we go. So you have a hello function. It tells, yeah, the name of the module and the function itself. And I suppose this is its arity, right? So, and then once you declare it, here comes the body of the function. So you can do different stuff in here. So as you can see, this function doesn't really do anything. Right, it moves literal hello world into the register X. By the way, Erlang is not a stack machine. It's not a stack machine. It is not a stack machine. It's a freaking register machine. So yeah. But you know what's funny? You know what's funny? It has thousands of X registers. So it has so-called X registers, right? So, and the way you refer to these registers actually is something like X0, X1, X2, X3, and so on and so forth. And I think you have around 1024 of them. Right. So you can kind of treat this array of registers as a stack if you want to. I mean, right, if you have a stack, the size of which is known at compile time, right, you know the size of the stack at compile time, you do not allow it to be like a dynamic stack or anything like that. You can just use this array of registers as the stack. I could implement this as a target for Porth, easy. Because one of the limitations that Porth has is that the size of the stack has to be known at compile time. That fits into the computation model of Porth, actually. So easy, actually fucking easy. So there's another like array of registers called Y registers. I don't remember what they're used for. I think they're used for manipulating an actual stack. On top of these registers, it also has its own stack, right? And I think, I don't remember, so I think it's needed for manipulating memory or something like that, right? I didn't fully understand, but I don't think we really need that. So in this thing, what does it do? It moves the literal hello world into the register X, and it just calls an external function IO format, right? So, and that's basically it. And if we take a look at the exactly what's going on here, right? So we're just calling IO format with the string literal. So yes. So it's pretty straightforward. So let's go back. Right, so this is the parameters that basically we can use, right, for generating the code section for bada bing, bada boom, bada bing, bada boom. Let's go ahead and do that. So I'm gonna just like do it like that. So let me maybe create something like chunk, right? So I'm gonna generate, starting from sub size, I'm gonna generate these things a little bit later, right? So that's gonna be basically the idea. Can I just like create variables out of these things, like a let, something like that? That would have been cool, I think. Right, so this is gonna be something like this. I'm gonna put semicolon in here, and I actually want to replace these commas with something like equal. Boom! Look at that. Do you like that? Do you like that, chat? I think it's pretty Polish. Right, so and in here we're gonna say it's U32. Right, so sub size is gonna be 16. It's gonna stay 16. Instruction set is gonna say 16. 0 opcode max, let's leave it as it is. We're not going to generate any code as of right now. We're not generating any code as of right now, so I suppose the amount of labels is going to be 0, right? And we're not going to generate any functions, so the function count is also going to be 0. That makes sense? Right, so that's the things we're going to have in our chunk. So let me just go ahead and extend this thing. So instruction set 2b bytes, and here, well, I mean, first it has to be sub size. Instruction set, then opcode max, then label count, then function count, right? So this is basically sort of like the preamble for the code chunk that we managed to generate. Then comes right, so where is the format? Then comes the code, and then comes the freaking padding. Okay. Oof. So the chungus has to be aligned by 4. So yeah, after generating a single chungus, we have to align this motherflipper by 4. So that means we'll have to append a bunch of zeros in case that thing is not divisible by 4. Right, essentially, right. Imagine you generated some sort of a chungus, right? So like this. How can you know if it is divisible by 4? Well, you split each individual element of this chungus into groups of 4. Okay, here's the first 4, here's another 4, and this thing is not divisible by 4 because, like, you see, there's like the tail, so-called remainder, right? So the tail of this group, and we call it in mathematical circles remainder, is not equal to 4. So we need to basically append like additional 0 to turn it like into this. Right, so this is what we need to do. After we generated a bunch of things, it still has to be aligned, it has to be padded by zeros, right? So it becomes divisible by 4. So maybe we can create a function called pad chunk, right? And it's going to literally accept the chunk, maybe a mutable vector of bytes, right? And it's basically going to just append a bunch of zeros. So the size of this chungus becomes divisible by 4, right? But to do that, we need to first know, is it already divisible by 4? Right, so we can take the size of the chungus, right, and do mod 4, and if it's equal to 0, it's already divisible by 4, nothing needs to be done. And by the way, mod 4 is essentially the size of this remainder, the size of this tail, after you try to divide this entire stuff by 4. Right, it's quite easy to get that little tail. That's what the mod operator for. It's literally the only purpose of this mod operator is to get this small little tail at the end when you're trying to group a certain number by a certain size. Right, so that's what it's needed for. Okay, if it's already equal to 0, that means like like we have nothing in here, it's already divisible by 4. So the only thing we care about is when it's not equal to 0, right? So that means, right, we need to append a certain amount of zeros. So in this case, the remainder is 3. So that means we need to append 1. Right, so essentially how many things we have to append? We have to append 4 minus this remainder. Right, minus this remainder, and I wonder if I can actually put that remainder into a separate variable. Can I call it like rem? And then I can do a rem, and then I can say for 0 to rem, right, just this amount of times push byte 0 into the chunks, and that's basically it. So that's how we can basically align that. That's very dumb, but I mean, we have to append 3 bytes at max. We have to append 3 bytes at max. Maybe there's something that allows us to repeat a certain byte for the slice, right? So can I, so there's a slice repeat. So you can repeat a certain, well, that's very interesting, right? So essentially, if you have a slice 0, you can say repeat that slice this amount of times, and then you can just extend that slice with this kind of thing. But if you repeat, you get a vector, right? So, but maybe that's fine, right? So, and essentially, if this thing is, yeah, okay. Is that better? That looks awful. So that means that's the solution we're gonna go with. That's the solution we're gonna go with, because it looks awful to piss more people off. Yes, kawaii freaking desu. So this thing has to be mutable, by the way. Okay, go. So we don't append anything, right? So the size of the code is going to be literally 0. Okay, so we're going to do chunk, you know, pad. Oh, and by the way, as far as I know, there is another really unpleasant thing about the beam format, is that the chunk size should contain the size of the chunk without the padding. Right, so this size does not include padding. It does not include padding. Right, so essentially, if I do something like pad chunk, right, and I just pad this specific chunk to 4, and then I want to generate a different chunk, right? So let's actually say, let's call this thing result, right, and then I'm gonna append, actually extend this entire thing with code as bytes, right, code as bytes, and then extend that stuff with the size of the chunk. I actually need to interpret it as U32, right, as U32, 2 bytes, and then I extend this entire thing with that chunk, right? So the reason why I do that is because, like, I need to first know the size of the chunk. Before I can put it in here, right? So first I generate the chunk, then I put the size of the chunk, and then I append it to the final thing that I return as the result in here. But here is the interesting thing. That size has to be unpadded. But I already padded it. So that means I have to pad it after I calculated it. It's kind of funny, isn't it? It's kind of funny. Anyway, so that's basically everything, right? Isn't it? I think that's basically everything. So let me try to compile, and it's compiled. Look at that. It actually compiled. So let me take a look at bada beam, bada boom, bada beam, bada boom, bada beam, bada boom. So yeah, there we go. So we have code. We've got the code. So the code starts somewhere here, right? So here's the code, and we have the size, and we have some other parameters in here. Right, and we have nothing at the end, right? So that's basically the beam file with the code, right? The beam file with the code. I ran out of tea actually. I ran out of tea, so I think I'm gonna make a small break. And after the break, after I have my cup of tea, we're gonna go ahead and continue slapping the code. Right. All right. So we have a code chungus, right? So we managed to generate the code chungus, and let me see if it compiles. It seems to be compiling. So if I take a look at that specific code chungus, right. So do we have anything in here? Okay. So we have something, and if I try to load it up in an Erlang virtual machine. All right, so let's do, where is the code loader? Okay, so it does not complain about the code table anymore. Can your chat GPT do that? I don't fucking think so, mate. Anyway, so let's generate the atom, the atoms chunk, right? So let's go into the parser. I want to extract the format of the atom chunk, atomic chunk. So an atom chunk is basically a list of strings, right? It's basically a list of strings. So let me put this stuff in here. Right, so we're gonna do it like that. Boom. Atom chunk. And we're gonna accept the list of atoms, right? So let's say we're gonna have a list of these slices, and we're gonna return a vector of bytes. So yeah, so essentially you have to provide the number of atoms, and then you put sequence of atoms, which is 1 byte per atom, which is the length of the atom, and then the atom bytes, the string itself. So these are sized strings. These are Pascal strings, by the way. These are Pascal strings, even down to the limitation of the size. So since you can only have 1 byte for the length of an atom, you cannot have an atom longer than 255. Let that sink in. Let that sink in. So yeah, let's go ahead and do that. So we're gonna have a mutable chunk, vector new, right? And so the first thing we have to do, we have to put a number of atoms in there, right? So we're ignoring this stuff for now because we don't know the size of the chunk yet. Right, so let's go ahead and do chunk extend the size of atoms as U32, and we're gonna do 2B bytes. 2B bytes, boom, we actually put that stuff in here. So let's start iterating atoms, like so. And for each atom, we're gonna take the length of the atom as a byte, right, we're gonna do 2B bytes, and we're gonna append that into the chungus. Append that into the chungus. And then we have to append the atom itself, right? So we have to take atom as bytes, and then we're just gonna do chunk extend, like so. And that is basically it. After that, we wanna pad the chunk, right? So we wanna pad the chunk, and then generate the rest of the stuff, the result. Okay, so that means we'll have to pad it after we generated the result, right? So the result is going to be another thing in here. Right, so we are extending the result with the atom as bytes, right? So here is the atom. Then with the size of the chunk, right? So chunk len as U32, so that's the size of the chunk, as say 2B bytes, and then we pad the chunk, and then we extend this entire thing with the chunk as well. So padding the chunk to 32 bits is extremely important. It is in fact extremely important. Oh boy, I hope I'm not gonna run into any of the roadblocks. We'll see how it goes. Okay, so I'm gonna append the atom chunk, and we can generate a bunch of atoms in here. So let's actually generate something like hello world and so on and so forth. So one of the chunks we'll need, by the way, we'll need the name of the module, right? So itself, right? Because we're going to be declaring imports and stuff like that. So Bada is probably one of the chunks that we want to have in here. So let's actually put it in there, right? So let's actually put it in there. So, and let's just run this entire thing, and it seemed to be working. Let's open a bada beam, a bada boom. And do we have any stuff in here? They go, here are the atoms. You can clearly see that before the atom, you have 1 byte, 1 byte, 1 byte, and that bytes is basically the size of the string. And as you can see, you have 3 bytes in here to bring all of that to like alignment by 4. And you can clearly see that there is alignment by 4 in the entire file. So the entire file is aligned by 4 because there's no remainders in here, right? So as you can see, it's just like groups of well, I mean, this is actually not really bytes, these are nibbles, but everything is perfectly aligned here. Everything is perfectly aligned. So it's a group by 4. Okay, so let's go into the Erlang and try to load this entire thing. So loading module Bada, please recompile this module with OTP bat file. Huh. It doesn't really say what exactly is going on. All right. So let me go into the Erlang and I'm going to try to load it up. That's kind of weird. So we may try to disassemble this entire thing. Beam disasm, that specific file. So this is going to be beam. Right, missing chunk XPT. Okay, so sometimes the loader is incapable of telling us what exactly is going on, and it's kind of nice to fall back to the disassembler because sometimes it can tell us some more information about what the fuck is going on. So another chunk that we need to provide is the exports chunk. All right, so yeah, without the, I wonder what it's going to say if I don't provide any atoms chunk, right? So let's actually try to do it like that, right? And in Erlang, if I try to disassemble it, it wants the atom chunk. But once you provided the atom chunk, right? Once you provided the atom chunk, the disassembler wants the exports chunk. I wonder what's going to happen if you don't provide any of the atoms. What if you don't provide any of the atoms? So there's no atoms in the final file. Ooh, this is funny actually. Holy shit. Extract atom. It was trying to extract an atom. It was trying to extract an atom and it couldn't do that. It was trying to do that in Latin 1. Oh, by the way, so when you do atom 1, you can only use Latin 1 encoding, right? So if you want to use UTF-8 encoding, you have to do at U8, right? So it's a special sort of like an atom chunk, special atom chunk for encoding UTF-8. So maybe that's the chunk we have to use, right? So, and apparently you can't have an empty atom chunk, which is kind of funny, right? So, yeah. Anyway, so if I do that, what's gonna happen if I try to load the empty chunk with the virtual machine? Corrupt atom table. Yeah. So atom table apparently may not be empty. Atom table apparently may not be empty. Otherwise, it's considered corrupt both by the virtual machine and the disassembler. And the disassembler. Okay, so we can try to maybe put something back like Bada in there. Maybe one atom. Maybe you need to have at least one atom. Right, so if you have one atom. Ooh. Missing import table. But it was complaining that the file is bad or something. Hello world. Okay, wasn't it complaining about that? So is that because I was using the atom thingy instead of UTF-8? instead of UTF-8. Yeah. If you're using non-UTF-8 atom table, it cannot load it. I suppose maybe it doesn't support non-UTF-8 atoms anymore. Wait, if I have non-UTF-8 but with Bada, it's also going to compile. You know what it feels like? Chat. You know what it feels like? It feels like a lockpicking, doesn't it? So I'm just changing I'm just changing a byte of like a bunch of bytes and see how the lock clicks and stuff like that. Like I'm observing like the outside effects without looking inside of it. Right, this is actually quite funny. Right, I'm changing the combination of bytes and see how the virtual machine reacts. That is quite freaking funny. Like I'm learning the system from the outside, right? So I'm learning a black box, right? I'm learning a black box without looking inside of it. If I start looking into the source code, this is gonna be already like a white box thingy. Right, exploring the maze, right. So I'm exploring the maze. So it's actually quite fun. I really enjoy that. So if I do Bada, okay. So apparently the modern Erlang VM does not support Atom like that because it's non-UTF-8. You have to use UTF-8, and it even tells you that. So error loading module Bada, please recompile this module with. You could have actually given me more information, motherfucker. Like, what's up with those people? Right. I suppose this message targets like the non-technical people that don't know how the internals of the Beam compiler works. Just don't think about that, you dummy dumb. Just recompile your silly file. You're not supposed to understand that. Like smarter people than you figured it out for you. Just recompile your file. Fucking. Could have at least tell me. They could have at least tell me that, bruh, we do not support the like Latin 1 encoding anymore, right? So this is an old compiler, just use a new one. They could have at least mentioned that, just like a glimpse of information for people who know what is going on. It's just like, come on, why are you treating me like a dummy? SMH my H, SMH my H. Okay, so we learned a couple of new things. First thing we learned, you're not supposed to use Atom with the modern Erlang VMs, right? You're supposed to use @U8. Second thing I learned is that Atom table cannot be empty, apparently. It cannot be empty. So another thing I kind of vaguely remember from the Beam book is that the Atom, like you refer to the Atom in the opcodes through the indices. And the minimum valid index for the Atom is 1, right? So the atoms are indexed starting from 1 in that specific table. You know why? You know why? You know why? This is because the atom 0 is actually nil. Atom 0 is a reserved atom, global atom across like all of the modules and stuff like that, and it's nil. And it's an atom 0, which makes sense actually. Which makes sense. It's pretty cool, I think. I think it's pretty cool. Anyways, all right. So what does it want? What does it want? What's the book? It's called Beam book. The Beam book. This one. It's literally a book dedicated to internals of Erlang. If you ever wanted to understand how internally Erlang system works, like opcodes, virtual machines, and stuff like that, the shit that we're doing right now, there is a book for that. Unfortunately, it's not finished, right? So there's a lot of chapters in here, and not all of them are finished. So, but it's kind of good for like a reference guide, right? So you have a table of like opcodes in there, some a little bit of descriptions and stuff like that. Okay, good. So the next chunk we need to generate, chat. The next chunk we need to generate is the imports chunk, right? So missing import table. So let's take a look how you generate the import table. Import chunk. So yeah, essentially you have import count, and then you have a sequence of triples, the module name, the function name, and arity. Module name is 32-bit integer. Function name is a 32-bit integer. How a name is a 32-bit integer? This is because that integer is an index in an atom table. That's why you have an atom table. Atom is a symbol, atom is the name, and you refer to these atoms throughout the entire file, right? So you say, okay, I'm importing the function with the module atom that one and function atom that one, right? And of course the arity, right? And this is actually the classical signature of a function in Erlang. The classical signature of the function in Erlang, where you have the module name slash the function name, actually colon, excuse me, module colon function name slash arity, right? It's like 69 or something like that, right? So this is the signature of a function, full signature of the function. It's 3 elements: module, where it's located, its name within the module, and its arity. And essentially that's an equivalent of that, but in binary. So that's why you should have your atoms before everything. Yeah, exactly. So, and because of that, this is a pretty straightforward format, right? So we have a count of those things, and you have these triples, and then they are repeated for the import counts. And of course, then you have to not forget to pad your chungus. Okay, but what is arity? It's the amount of arguments. It's a mathematical term. If you Google up what is arity, snap back to reality. Here comes arity. So in logic, mathematics, and computer science, arity is the number of arguments or operands taken by a function, operation, or relation. That's what it is. It's just a number of arguments. So let's go ahead and generate this shites. So did I already copy paste this stuff? So imports chungus. So I suppose for now we're not going to generate any imports, right? So I want to create an empty module, right? Imports chungus. Okay, so here's the imports chungus. So, and we're gonna just return vec like so. Mutable chunk vec new. In the chunk extend, import count is going to be 0. Let's actually maybe define it like that. Import count 2 bytes. Let import count u32 0. Nothing in there, but in the future we're going to actually extend it. That's it, I suppose. That is basically it. So we need to create the result, which is also going to be vector new. Right, then result extend imp t as bytes result the chunk size. Okay. Chunk len as u32 2 bytes. Then pad chunk, mutable chunk, and extend the chunk, and then just return. So after that, we can extend the beam file with the imports chunk. It's actually kind of cool how easy it is to add like additional things in here. Yeah, so we just implemented a new chunk. And then in the future, all of these functions may be parameterized with like a more high-level arrays of structures, right? So maybe we're going to have a structure import, right? Structure import, right? And it's going to be literally just a module, which is going to be a string, function, which is going to be a string, and arity, usize, and maybe it's going to have some sort of a function, right, that renders that entire thing into a sequence of bytes, right? A sequence of bytes. Just a second. Given the list of atoms, something like this. You know what I'm talking about? Right. So on a level of like logic, high level logic, you operate with like real names and stuff like that. And then you can render it down to a sequence of bytes, knowing the atoms, right? Because it's going to look up each individual model in the atoms and stuff like that. Maybe this entire thing is going to be actually mutable vector of these things. So if, for example, during the rendering, you encounter a thing that is not in the atoms table, it's going to automatically append it to the atoms table. So then you can render your atoms table. So, and because of that, this could be something like a hash set, maybe hash map from str to u32 or something like that, right? So then if you encounter a new thing that was not in the atoms before, like I'm getting too much ahead of myself, right? So you can clearly see like how you can develop this entire system that automatically collects and generates and stuff like that. So I should probably not go ahead of myself. This is the main trap of this kind of project, is that you're trying to go ahead of yourself and like start over engineering the system, and then you can get yourself into the trap where it's very difficult to get out of, because you created such a beautiful system. It would be really, you're gonna feel really bad for tearing it down when it doesn't work out for you, right? So that's why I don't really like to architecture ahead of myself, right? I only architecture when it's actually needed, when it's been proven that, yeah, that's exactly what we need for that specific case. This is just speculation. Having this system that automatically keeps tracks of atoms is just a speculation. This is just like a me from 10 years ago speaking right now, right, who is inexperienced and want to over-engineer shit and Haskell and stuff like that. I should tame myself. Okay, we need to only implement things that are needed right now. So, all right. Let me see. So we created the import chunk. We already, all right. So let me see if I can now load this entire thing in here. Export table. Okay. So it does not complain about import table anymore. Okay, so, and the cool thing about the export table is that it's kind of similar to import table, actually. It's literally the same. It's just like a different name. So, as you can see, you have, well, I mean, you don't have to provide, you don't have to provide the module name, because it's obviously with the module you are in. You have to provide the function name, the arity, and the label. In the label. So an label is basically the label within the code chunk where you have to jump. If you take a look at the disassembly of the hello function, right? So beam disassemble file hello beam. Right, so for each individual function, right, you have label 1, label 2, and stuff like that, these kind of labels. So in reality, the code block is a continuous sequence of opcodes. It's a continuous sequence of instructions, and all of the bodies of all of the functions are just concatenated together, right? So it's just like a continuous sequence of instructions, and the start of the body of the function is denoted by a label, right? You literally place these labels in here, and label is a special instruction that is going to be removed during the loading, right? It's needed only to mark the places within the code. And in the export, you also specify the label where the function starts, right? It's usually this one, I think that it's that one, right before the function info, because after you call the function, you need to encounter, I think you need to encounter function info, so the runtime knows what kind of function it is executed, because it's setting up information for the runtime error generation, right? So it's sort of like a preamble for the function. So then when an exception happens, it knows what kind of name of the function to put in a stack or something like that. So it's kind of important for the execution to encounter this specific instruction. So func_info is an instruction, by the way, right? It's a very high level virtual machine. Label is the instruction. Func_info that tells you about the current function is an instruction. And then you have moves and stuff like that. Line, I don't quite remember what the fuck is line, but I think it's also for debugging purposes, right? It's also for debugging purposes. You know, Erlang comes with its own debugger, and it's the funniest shit ever. I still haven't figured out how to use it. Right, but I can show you Erlang. Just a second. Debugger start. This is how you start the debugger. And it opens up a GUI fucking application. Imagine like you're in a terminal, you start debugger start, and this is a GUI application, right? So it's just like it's a debugger. Yeah. I don't know how to use this shit, by the way. It's just like you have like checkpoints and stuff like that, and then you can close it. So fucking funny. Like I was googling up how to debug like Erlang and stuff like that. I found that this is what you have to do, and I got like almost spooked out. It's just like I didn't expect. Like I thought I'm working in a terminal. It's just like a GUI window pops up. Like what the fuck is going on? What? What the fuck? So when I was writing Erlang for living, we would do process info calls and inspect state, etc. I never used that GUI. Okay, I'll make a note. I have no idea what you're talking about, by the way, but I'll make a note that maybe process info is something more useful in this specific case. Okay, so what do we wanna do? So we need to generate the expert table, right? So let me quickly maybe copy paste this entire stuff, right? Let me quickly copy paste this entire stuff. Right. So what I'm thinking is that maybe I'm gonna also copy paste the import chunk, right? Because it's kind of similar if you think about that. So we're not gonna export anything, but we can query replace import with export, right? So this is gonna be export count, and we also have to change this thing. There we go. So we have to change this thing. So okay, so we never call this. So let's actually put it in here, exports. I think that is basically it. So we also need to have string literals, if I'm not mistaken. String literals also mandatory chunk. Right. So let's go. Let's try to load Bada invalid opcode. Okay, that is very interesting. So maybe right. So maybe we have to actually put something in a code block. Put something in a code block. All right. It doesn't really tell us what's exactly. Let's try to do disassembler. Beam disasm file bada bim bada boom bada bim bada boom boom. Missing chunk. Okay, so that's pretty interesting. So the virtual machine complains about the code, right? The invalid opcodes and stuff like that, but the disassembler complains about the lack of strt. Okay, so let's actually maybe try to satisfy the assembler first, right? So where is my parser? So strt. And strt is very simple. So it basically stores these strings, right? It stores the strings. And if you don't have any strings, you can just leave this thing empty, right? It's not that big of a deal. And you store all the strings in a continuous chunk, right? So it's just continuous chunks. So should be easy to generate as well, given that we have a huge experience in this stuff, in generating the chungus. There we go, string chungus fn, right? So we're gonna just return this kind of thing. Let chunk vector new. It's mutable. Chunk. So data. That's gonna be literally nothing. And 0 is already padded to... Yeah, we don't need any of this shit, I think. I think we don't, right? So I can do chunk extend strt as bytes, and then chunk extend 0 u32 to be bytes, and then just that, right? Because I don't have any data, so... And 0 is already padded by 4. Right, so that makes sense. It's just like, yeah. Okay, so string chunk. What else do we have in here? Erlang. And let's try to disassemble this entire thing. empty code segment. Okay, so you can't have empty code segments either. It's kind of funny that it first checked for all of the segments and only then started to complain about empty code segment, but then it complained about empty atom segment right away. Isn't that kind of funny? Isn't that kind of, I think it's kind of funny, right? It's just like different checks for the, like, verification checks for the correctness of the format are happening at different times. It's just like, it's kind of funny to see. So you can't have an empty code segment. So we can try to put maybe a label in there, right? So we can put a label in there, like an instruction. Okay, here's the thing about instructions, right? So let's actually find. Instructions consist of first opcode, and opcode is 1 byte. Right, so instructions start with 1 byte and it's opcode. All of the opcode numbers are located in beam opcodes URL. Here they are. Right, label just marks the location within the code. So, and it's just like a code 1. Then, depending on the arity of that opcode, opcodes also have arity. You have a certain amount of arguments, and arguments have variable length. They have variable length depending on their size. And each argument is just a number. It's just a number. Depending on the size of the number, it's going to be encoded with a variable amount of bytes. But on top of argument being a number, it also has a tag associated with that number, which denotes its type. Right, so we can actually maybe describe the format of the instruction like so, right? So we have an opcode, which is just a byte. Then you have an argument, right, which is basically a tag plus value. And depending on the arity of the opcode, of that opcode, you have a variable amount of such arguments, like so. And what kind of tags do you have? What kind of tags do you have? Compact, here it is, compact, term encoding. So you have a tag literal, integer, atom, X register, Y register, label, character, and so on and so forth. So basically that tag describes what that value means in here, right? So for instance, the label, well, some like a move instruction, for instance, it may accept a register. It may accept a register, and for example, in that case, tag is going to be X tag, right? So I was thinking, why the fuck do you need tags? Why the fuck do you need tags? Can't you just say, okay, opcode decides what that specific argument means? But I just realized now, move instruction as an argument may accept either immediate value, an integer, just a value, or a register. So depending on the tag, it's gonna interpret that value differently, right? So because move can get its source either from a register or it's an immediate value. So that makes sense. Right, and the main ass of the whole thing is how you encode the argument, the tag plus value, how you encode them, right? And here comes the most anal way to encode like arguments you've ever seen in your entire life. So again, if the value is less than 16, then you encode that value within the upper 5 bits of the tag. You literally fuse the tag and the value. So, oh boy, right. I mean, this kind of hurts. Well, it is what it is, and it isn't what it isn't. The algorithm, I mean, that encodes and stuff like that, actually it's available, right? So beam encode, beam asm encode. Here it is. So it's 1, 1, and there you go. We can even take a look at that. So we have a bin opcodes. So asm Erlang. Okay, so and we should have a function encode. So it's probably somewhere in code. Yeah, there we go. Okay, so here is the function that does the encoding, right? So there's you provide the tag, and if I'm not mistaken, the tags I already showed where you can find the tags, opcodes, HRL. So here are all of the tags, right? So you have 8 of the tags. You provide the tags and you provide the value. For the negative numbers, you can encode negative numbers with this shit, yes. So you have a special way of encoding them, right? And it's somewhere down there, right? So it's a special way of encoding them. If it's positive, right, but less than 16, it's pretty straightforward. It's actually a very easy case, right? You just smash the value and the tag together, right? If it's greater than 16 but less than this number, you use 2 bytes to encode that. So here is the formula that performs the encoding for 2 bytes. So here is the first byte with some masks and stuff like that, and here is the second byte. And if it's bigger than that, right, so we can even take a look at what's that value. Bigger than what? Just a second. 080 to 2000, right? So this value is 2000. It's bigger than that. Use a special different encoding in code 1, right? So, and this one is rather I don't even fucking know what it does. I think it's a right. So there's like additional functions, and as far as I know, if I understood correctly, like all of these codes, yeah, so the algorithm to encode the argument is basically, yeah, it's basically this. It's basically this. Bor. I suppose it's binary, like a bitwise OR, yeah. So there's also things like BSL, which I can only guess bitwise shift left, right? I don't know Erlang that much, but I can guess that it's a bitwise shift left. There's also BSR, which is probably bitwise shift right. Bor. To be fair, so this is the entirety of the algorithm, right? Sorry. So this is the entirety algorithm. Algorithm is not that complex, but it's not that simple either. Right, it's not that simple either. So one of the things we can do, we can actually implement it incrementally. So essentially, we can implement it only for n less than 16, right? And for today's stream, we're not going to use values bigger than 16. Do we really need bigger than 16? We need to encode 69 somehow, for obvious reasons. For obvious reasons, we need to encode the 69 somehow. So we'll see. But anyway, so let me see. I have an idea. What if I just take the OpCode and put them in here? So enum a tag. So in here I'm gonna replace that with comma, and this shit I'm gonna replace it with this. Can I now do something like this? Get a tag. So, but I want this to be like a byte, a single byte, but maybe it doesn't really matter. So the thing we can do, we can say encode tag, and then n, and n could be usize, but it also could be negative. So let's actually say i32, right? So, and in here we're gonna return a vector of bytes, right? So depending on the value of the n, it's going to be encoded with different stuff, right? It's going to be encoded with different stuff. Okay, so what if I go to asm and maybe I'm gonna just put an assertion in there. So if n is negative, I'm gonna do to do negative, right? So this is not implemented. Else if n is less than 16, right? Less than 16, we can literally just copy paste this stuff in here, right? Can't we? So let's say that tag is gonna be tag as u8, right? So we're gonna interpret it as a byte, and then n is gonna be n as u8. All of that is just bytes, right? So bit shift left, so n4, right? n4 tag, and just like this. So, and then else large numbers. We can do something like that, right? So unless we encounter something that is bigger, right? So I don't freaking know. So all right. So how do we do that? Where's the code chunk? Code chunk. Code chungus. So function count. After the function count, the code starts. After the function count, the code starts. Let's say chunk push, and we need to put the opcode for the label there. What's the opcode for the label? It's actually 1, right? So I need to put 1 in here, and then I'm gonna do chunk push, and for the label I don't remember what's the label has to be. Is it has to be? There's already a label in here, but I think it's used for referring to the label. I think it has to be an integer. So let's actually try to use an integer in there. So encode tag I. So we can also like see what kind of errors that encounter, hopefully. And they have to start with 1. I vaguely remember from the book that labels also start with 1, right? So atoms start with 1 because 0 is a nil, and labels also start with 1. You know why? Because label 0 is considered no label or invalid label. Why do you need a no label or invalid label? There are instructions, very interesting instructions. So there's a list of instructions in there. So generic instructions, I think it's something like gcbeef2. Right, so it's basically call to a built-in function. So beef stands for built-in function. They have interesting arguments. They have arguments LBL, label. And label is where to jump if the built-in function fails. On failure, jump to LBL. Right, so in your code, you can generate error handlers. You can generate error handlers to which a certain functions will jump in case of an error. So if you don't have an error handler, you can put a label 0 in there, and that's an invalid label, and that will generate some sort of runtime error. So I suppose this kind of stuff may be needed for try-catch things. Maybe that's an interesting, yeah. Essentially, if you compile and try-catch block, or every call to built-in function or maybe not built-in function that accepts a label where to jump in case of an error, you can set a label to the catch section, and that kind of automatically, that kind of translates from Erlang to the bytecode nicely. I think that's why it is like that. So, and again, labels start with 1 because label 0 is that means you don't have any label, you don't have any place to jump to. So yeah. So let's put it like that. So to be fair, like referring to the opcodes with numbers is kind of meh. What if we had like an opcode enumeration as well, similar to the tag enumeration? All right, so we're starting to build up our own Beam library, chat. Our own Beam library. Isn't that Pors? Isn't that Pors? OpCode, mother flippers. OpCode. And here we're gonna have label, and it's just 1. So, and here I can just do opcode label as u8. Can I also say that I want to use u8 as an internal representation for the enumeration? Can I do that in Rust? Can I do that in Rust? underlying type for enum. So internal type, inner. Oh yeah, I remember. They couldn't come up with the syntax for that. Thank you so much. I vaguely remember that. Yes. It's goofy like that. There is no syntax for this thing, so they just whatever. Just slap an attribute on that. Like, I mean, we can't update our parser. Our parser is too complicated for this kind of shit. Just slap an attribute on that. Anyways. So yes. But I mean, it's probably not that important for us, to be fair. Encode mismatch types. So extend. All right. So we have a lot of unused to get freaking damn it. Okay. Can I just comment out all this shit, brother? Yeah, let's go to Erlang. And what we were doing here, we were trying to disassemble this entire thing. No func info encode segment. Okay. That's really funny. So, okay, so you must have something in there. You must have something in there. That's so funny. Okay, so usually, like, you have a label, func info, and some other stuff. So for the func info, you have atom, and 0. I suppose it's Arity. Snap back to reality. So, oh, here it is. MFA. Func info MFA. Define a function. Okay, it is Arity. Motherfucking Arity. Alright, so let's go ahead and try to do that. So, func info. Here it is. It's the second one. It's funny how these are the first instructions in Erlang VM. So that means they're most important. Is label and function information. Not like push data or something like, or move data. No, this is just like label and func info. Int code end. Anyway, so we need to have a func info. So this is going to be 2. Label. All right, chunk push opcode func info as you ate. So, and the first thing has to be an atom. Right, encode, and for the atoms, I think we have a compact. Yeah, tag A is an atom. And atoms are numbered starting from 1. So, and this is the name of the module. So we already have Bada in there, right? So that means we can put A in here. And what's funny is that maybe in the future we're gonna accept atoms in here, right? And then I'll be able to just query this kind of stuff. Oh, okay, I'm getting ahead of myself too much. Alright, I'm getting ahead of myself. But we can actually have Bada function within the Bada module. Yeah, so we can do that, right? So it means we can do 1, and that refers to the same atom. So it's we're using the same atom both for the name of the module and for the function. So, and I suppose for the reality, we're gonna have integer in here. So there you go. So we have a label and we have a function info. Are you happy now? As far as now, you need another label in here to sort of like to denote where the body starts. And as far as I know, in OpCodes, you also have a return, right? And that returns from the function. So we might as well put a return in here just in case. So am I getting ahead myself once again? So I think it's kind of dangerous. It's not 3, it's actually 19. So let's see if it's going to actually help with anything. So there's no A in here. All right, so IA, okay. So it generated some shites. Let's see Bada bim, bada boom. I0, function close, invalid resolve arg unsigned. Okay, wait. Unsigned. So it was trying to resolve an unsigned argument, but it encountered a signed one. So maybe we're supposed to use this one. So tag I. So there was a 0. So for the function info, it wants to have U in here? Is that what it wants? Maybe we have to use U for labels as well, because I don't expect the labels to be negative. Okay, so U is not really... This thing says that U is a literal and I is an integer, but U is... I suppose U is unsigned. It's unsigned, right? That makes sense, I think. So unsigned, signed, atom, X register, Y register, F is a label, H is a character, and Z, I think it's extended or something. I don't remember what is Z, because there is extended stuff like a float, list, floating. We're probably not going to go into this complicated shit today, but yeah. So I think that's what it is. Okay, so let's try to compile this entire stuff and okay. Function Bada, label 1, function for Bada 0 Arity, label return. But this is only the disassembler. So we are capable of generating the instructions already. And we didn't even have to implement the full anal way of encoding, right? Because we don't use like numbers bigger than 16. Numbers that are bigger than 16. So we don't go that deep into the anal encoding, right? We don't have to go that deep. All right, so the disassembler seems to be happy. What about the virtual machine itself, right? Can we load the Bada? Okay. Ooh, invalid label number. We have a label count. Do you guys remember a label? Fuck. I forgot about that. That's funny how Disassembler didn't care about that. That's actually kind of funny. Well, I mean, we have 2 labels, right? So there's 2 labels. And since we're having a function, I suppose there's 1 function in here, I guess. So far so good, right? So let's try to compile this into a thing, and boom. Op aligned label num. That's bizarre. So tag you. Do you want the label to be? Let's put 3 in there then. That's a bit bizarre. So do you mean that the label 0 is a valid label in that case? Maybe I misunderstood the documentation. Invalid OpCode. Okay, that's bizarre. Invalid OpCode. Oh, wait. Code segment did not end with encode, and I remember seeing that. Wait a second. Int. Yeah. You denote the end of the code section with this one. All right. And its arity has 0, so you don't have to do anything. Okay, that's cool. So let me see. So we have that. 3. Code chungus. Here's the code chungus. So chunk push opcode int code. Why is it called int code? And interrupt integer. I don't freaking know. Okay. So those we have. no warning anymore. So there was a warning, now there's no warning. So everything seems to be fine. Okay, so if I try to load this, we just loaded module. Thank you, everyone. Okay, so here's an interesting thing. There's no Bada function in here. There's no Bada function in here. Actually, every module that you load, it always has at least a function called module info. Right. So which prints the information about the module. Right. But Bada doesn't have that thing. So, and this is something interesting. The reason why every module has module info is because of the Erlang compiler. It is not something that is built into the virtual machine of Erlang. It's something that is built into the Erlang compiler. If Erlang compiler didn't generate that function, it would not exist, right? So you can take a look at the module hello.erl, right? So it doesn't implement anything but hello, right? But if you take a look at module info, right, and what it exports, it actually exports not only hello, but also module info with Arity 0 and module info with Arity 1. So the Erlang compiler generated those additional functions for you implicitly. But since we now generate everything, we don't generate that, so there is no such functions in the module. This is kind of interesting. So if you take a look at the assembler, disassembler, build disasm file hello beam, and you would see how these functions are implemented. So here are the functions within hello. Here's the hello, which just calls hello, and then you have module info. So what does it do? So this is a standard preamble of the function. Then it moves atom hello into the register X and calls external function called Erlang get module info. Even if the module doesn't have module info, you can still get information about the module if you call this function directly. Honestly, I have no idea why the fuck Erlang compiler generates this function. Because what it does, it just calls to the standard get module info function. Like, why? It's kind of silly. It's kind of goofy, but you insert this thing into every module, and it's just like, I mean, okay. So I can't do module info. I can't do module info, but I can do Erlang get module info Bada, and I can get module info for the Bada. So, and we can notice that Bada doesn't export anything. Even though internally it does have a single function called Bada, it doesn't export it. It does not export that function. So that's why you can't call Bada. So to make this function accessible, we need to export it. So let me see what we can do about that. So where is the exports chunk? So exporting thing is rather straightforward, right? So it's a function name, Arity, and the label. Right, so we know that it starts at label 1 or something. So okay, so export is going to be 1. So next thing is going to be chunk, extend, function name. Function name is an atom. We already have one atom Bada in there, right? So here's the atom Bada. So that means that it's an atom 1, 32, 2 B bytes. Right, 2 B bytes. So the next thing has to be the Arity. Right, Arity is 0 in our case, so it doesn't accept anything. And the label, so let's see. I don't remember which label you have to provide exactly. I don't really remember. Where's the code chunk? Code chunk. Okay. So the label before funcInfo or the label after funcInfo? I don't quite remember, honestly. I think it's the label before funcInfo because the runtime needs to get information about function before starting executing it. it's needed for the debug purposes or something like that. So I think we have to jump to the label 1 rather than the label 2. To be fair, I'm not really sure why you need the second label. It kind of denotes the body. But maybe it's needed for, I think I know what it's needed for. It's probably needed for tail call optimization, right? When you have a tail call recursion, right? When the function calls itself in a tail call way, it's probably not calling the function, it's probably jumping to the beginning of the body like that. So that's probably why Erlang compiler generates this additional label at the beginning of the function body. This is my hypothesis. I don't really know for sure, but if I were implementing Erlang, I probably would do it like that. So yeah, so because of that, we have to jump to the label 1 if we're going to be expert in that specific function. Exports chunk. All right, so chunk extend 132 to be bytes. So this is the label 1, and that's it. Right, so now export count, blah blah blah. So let's try to recompile this entire thing. So it complains about this thing not used. So okay, so for now we use only unsigned integers and atoms. Erlang is heavy on TCO. Yes, it is, because it doesn't have loops like at all. It does have list comprehensions, right? So you can kind of say that it's kind of loops, but generally doesn't have anything for looping. So you must use tail call because it's better. So I think there was a funny tweet about that on Twitter recently. Does anybody know? I think it was about a camel. So the sign was recursion is better than for loops because there's no modifications, so like, and there is no state, so it's very easy to reason about recursion, and it's just like very complicated camel code that doesn't use for loops, and it's just like pure recursion is just like a recursive spaghetti if you ever seen one, right? It was so fucking funny because I programmed in a purely functional style very complicated shit, and I know precisely what people are talking about. Like, you can have spaghetti code in a pure functional code with recursion. It's fucking insane that you can have spaghetti code like that, but you can. And sometimes it's just way more readable to just do for loop, believe it or not. So purely functional recursive spaghetti. Did AOC and Haskell is pure spaghetti? Yeah, it's insane because you wouldn't even expect that. You wouldn't even expect, after all of these promises of easy to reason code, no side effects, ponies and unicorns, and it's just like, oh my god, it's just like, and you look at that, holy fucking shit. So all of that is a lie. All of that is a lie. Don't believe those goddamn functional programmers. They're literally lying to you. They're not only lying to you, they're lying to themselves. Anyways, so what do we have in here? So we generated the export. So let's see what we have in here. So let's try to reload the module. Where's the code? Okay, so we managed to reload the code, and now if I try to get module info, look at that, bada zero export, bada beam, bada boom. So can I do bada? But it's there. So and it's a 0. Huh. So get module info. I can try to disassemble that as well. Beam disasm. Maybe I have to put something into the return, right? So the values are returned through the X register, if I'm not mistaken, right? So disasm file bada beam. Because the arity is 0 here. The arity is 0. So the function 0, what is 2 though? What is 2 though? Okay. Experts. Function Arity, so function 1, Arity 0, label 1, then code chunk, function info, atom, that one, Arity 0, that makes sense. So let's try to maybe move something into the X register. So let me see. Generic, where is the generic instructions? Generic instructions, there was a move instruction somewhere there. Okay, so move the source to the destination register. Okay, so yeah, let's give it a try. OpCode, move 64. Okay. OpCode move 64. Before return, chunk x push opcode return move. Excuse me. So, and the first thing is the source. The source, we can put maybe a value. 69, we can't encode 69 because it's bigger than 16. So we can probably put something like 6, right? So this is going to be tag u6, right? So this is the source. The destination is going to be chunk push, and it's going to be a register. The register through which we return things is x, right? And it's 0s 1, right? It's the 0s 1. So we're going to move 6 into the register x, and hopefully that is going to be returned from the function. So we're programming in assembly basically, almost directly. We're programming in assembly almost directly. Okay, so this one has to be as u8. What else do we want in here? So this one has to be more like extend. And this one, x is not available, so let's make it available. Okay, so Erlang. Can I just recompile? Let's actually do disassemble. So disassemble. Okay, that's cool. So that recognized by disassembler, move 6 into x, right? So move 6 into x and then return. So we can even double check if that is the case with hello, right? So 6, right? If you just return 6 out of the function, right? So what is going to happen? So 6, 0. And then I can try to disassemble hello. 6. Oh, but this one uses integers specifically, and I think integer is the tag I. Tag I. So maybe that's the tag we have to use. So this is going to be tag I, tag u6. So let's say tag I. Okay, disassemble Bada. Yeah, so now this one uses integer 6 and moves it in there. Okay, so code load file Bada. Not purged. Oof. I remember. I think like you can't really reload already loaded module unless it was first purged. Whatever the fuck that means. Okay, so Erlang purge module. Because I don't know why, honestly. It's freaking Erlang. Oh, I think there's a function for that. Purge 1, yeah. There's even soft purge. So purge is the code for module that is removes the code marked as old. If some processes still linger in the old code, these processes are killed before the code is removed. I see. So maybe you have some processes that still use it, right? So that's why it needs to be purged explicitly and stuff like that. Okay, so I suppose we're gonna do code purge Bada, and then we're gonna load the code. We can even do something pretty cool because we can chain operations together, right? So load file Bada, boom, and that purges and loads a new version simultaneously, right? Because a comma is a single operator. Essentially, so can I do Bada, boom? That didn't help, honestly. That didn't help. So we have a function, but we can't return shit from this function. So we can't return shit from this function. So let me see if I forgot to do something. Did I forget to do something about that? So OpCode max label count 3, function count 1. Did I forget maybe align things? So did I forget to align things? I don't freaking know. Maybe I have to jump to a different... Okay. What if I have to jump to a different label? There's also... What if I set label 2? Exports. Label. So let's say if I set label 2 in here. Maybe that's the label problem. So let's just try to purge and... Apparently I was wrong about the tables. Bro. So what was the problem? Let me show you. So I need to disassemble the file. Let's disassemble. So essentially, there's two labels before the func.info and after func.info. The reason why I put two labels before and after is because the Erlang compiler does so. So I have no idea why. I'm just repeating after Erlang compiler. Right, so I thought that the beginning of the function, like the label that you have to put in the export as the beginning of the function, is the one before func.info. Apparently I was wrong. So I just changed it to label 2, right, which skips func.info, and it worked. So yeah, I don't freaking know. So so the problem with all of this stuff is that it's half-ass documented, right? Even the Beam book is not finished, right? So there's a lot of things here that are straight up not documented, right? So especially the further chapters, some of them say to be done or something, right? So not everything in here is documented. So the shell, so there's some stuff in here that is just like missing. So, and like a lot of the stuff you either have to get from the code or guess or something like that. So I wonder if people who have a lot of knowledge about this system, they get probably paid really well because they're pretty serious systems that rely upon this shit. I think you can actually get a lot of money by knowing all of that stuff, I feel like. Right, because there's probably some complicated telecom systems that use all of that stuff and they need people who understand this. It's actually a pretty cool idea. Maybe I should just learn all of that shit purely for the money. How do you dig up such exotic languages? Dude! If you think Erlang is an exotic language, you probably only recently started to program. Erlang is not an exotic language. It's older than Python, and it's like it's industry standard for telecom. You're just not aware of it. It's not an exotic language. It's a freaking standard. So I wouldn't call Erlang an exotic language, honestly. Erlang is not used in telecom anymore, but Cisco is using it. That's very interesting. Why is it not used in telecom anymore? Right, I mean, it's actually pretty well suited for it. Elixir is very popular in it. Why do I need Elixir? I can write my own compiler into the Erlang virtual machine. It's too easy. Too easy. Piece of cake. So the only difficulty is encoding of the arguments. Okay. So this is like an unsolved computer science problem: is implementing the encoding for the arguments of the virtual machine of Erlang. But I think we can do that. I think we can port the second case. I think porting this case is not that hard, honestly. I think we can do that. I think we can do that. So let's actually go ahead and do that. So essentially, what we want to be able to do. So code chungus. We are trying to return not 6 but 69. If you try to compile this entire thing, it will crash because not implemented large numbers. We don't know how to encode large numbers. Right. So we can implement very specific large numbers that are less than these ones. And to implement them, we just need to port this specific thing, this specific line. Okay. So so we're actually, first of all, we take n. Right, and since it's a positive number, I might as well actually maybe say that it's going to be U32. Then I'm shifting that number to the right by 3 bytes. Right, so that's the first thing I do. I take n, I shift it to the right by 3 bytes, and I do band with this mask. So I'm banding that mother flipper with this specific mask, like so. So I just band it. Okay, so we get that. Then I bore it with a tag, right? I bore, well, I mean, I have to do it like that. So tag, let's say the tag is going to be as U32. So tag, and then I bore it again with this mask. I just bore this shit again with this mask. So it actually has to be B. Excuse me, it has to be B. It also probably has to be U32. So did I copy the mask correctly? I feel like I want to recopy 0b, boom, U32. Okay, this is the first byte. This is the first byte as U8. Okay. I have no idea what any of that means, but do I really need to know that? I don't think I need to know that. So the second byte. The second byte is this. So I'm taking n and I'm banding it with just this. FF. Right, as U8. Okay, and so that is basically the encoding. So I probably made a mistake somewhere. But I mean, so that will allow us to encode the values up until 2048, which is actually quite a lot. Like, do we even need larger numbers, at least for now? So 2048 is gonna like last us for quite some time already, I think. And it's only gonna be like for immediate values, right? So we don't need these large numbers for doing large computations, right? Because if you accept large numbers through registers, you're just passing them along between registers, so you don't need to operate on such large numbers immediately. So like we quite rarely would need that. Negative numbers, they would be needed, but I implemented an entire self-hosted language without negative numbers. So negative numbers are not that much of a necessity. In fact, humanity, civilization, lived quite comfortably for a very long time without invention of negative numbers. People were doing math and arithmetics and economy and stuff like that without negative numbers for quite some time. So you can live without negative numbers. Like I'm saying that unironically, actually. The same way you can live without imaginary numbers. So yeah, so I think for now, this encoding is more than sufficient, right? So, and we can implement the rest of these cases like later. So I think that makes sense. So you come to the boss and boss asks you, why didn't you implement negative numbers for our new programming language that we sell into our customers? And you be like, you know, humanity didn't invent negative numbers. Anyways. Job security, yeah, exactly. And then you're fired, exactly. So, okay, so that means we should be able to now encode a 69. Okay, let's see if we manage to do that. So, I probably fucked something up. Look at that. We actually did it successfully, it worked. Okay. That encoding, well, I mean, even though it is anal, it is not as scary as I thought. Okay, so, all right. So the only scary part are negative cases and the numbers that are bigger than 2000, right? So, and if you are within the range of like 2000, it's actually not that scary. It's just a couple of formulas that you can just retype. So, all right, that's pretty cool. Okay, so let's just try to purge this mother flipper. Bada beam, bada boom. 69. That's pretty cool, actually. It's pretty cool. What the fuck? The most funny part is that we generated it entirely in a language that has nothing to do with Erlang. This language, like, we just generated it in Rust, so we sort of like cracked the code, and we didn't use any of the built-in Erlang facilities. Right, it's just like, it's a Rust file that uses only two things. Two things. Who can tell me what kind of things does this file use? Vector and write. You don't need anything else to write a compiler for Erlang virtual machine. You need vector and write. And I just demonstrated to you. Like, it's just like, it's too easy. You can add a read into that, and then you can read a certain file, all right? And you can then compile that file down to something. So you can maybe even invent some sort of a language, test language Bada, and obviously we don't really have that big of a generation capabilities as of right now. We don't really have very big generation capabilities, but we can invent sort of like a programming language that lets you define Erlang functions and assign numbers into them. You know what I mean? Then it collects all of these functions and like literally generates like Erlang module with these functions that return this number. We can already do that. It's a dumb language. It's the stupidest language you can come up with, but it's a legit language, and it will compile down to Erlang virtual machine. You can technically do that. How much time will it take for us to implement that? How much time will it take to implement for us? I kind of want to do that. But I mean, already streaming for 3 hours, but I need to make a small break, right? So let's make a small break. I'm gonna make a cup of tea. And once I have a cup of tea, we're gonna try to tackle the task of parsing this file and then generating Erlang module out of that file with all of these functions and shit like that. So, and once you have that, you can start extending the syntax by adding maybe, I don't know, like sequence of numbers, and then plus operations and stuff like that. I mean, who knows, right? So you need a point from which you can start and stuff. Camera noises or just me? Yes, there are some camera noises. Like I live in the Novosibirsk near the nuclear institution. I'm not even joking. We have the nuclear research institution like nearby. So, like, I'm not joking, we do have a nuclear research institution here. Within Novosibirsk, there are rumors that those motherfuckers hide a nuclear reactor. It's the funniest shit ever. So there are rumors that there is somewhere a nuclear reactor. And every time somebody asks this goddamn scientist, they say, no, there's no nuclear reactor, nowhere, but we fucking know. We fucking know these motherfuckers are hiding nuclear reactors somewhere. Anyway, so let's make some break. All right. So let's actually not start with parsing this shite. Let's start with not parsing it. So I think what I'm gonna start with is actually with defining a hash table, right? So we're gonna have a hash table, which is gonna be, let's call it a program, right? So this is a program, hash new. So maybe I'm gonna actually say that it's a mapping from a slice, a string slice to a number, right? So usize or something like that. And we're going to basically push a bunch of things in there. So we're going to push hello, which is going to be 69, and the world, which is going to be 420, right? And we're going to just restructure, like massage the code to compile this hash map, into the beam module. Right. So essentially, we're going to assume that all of that stuff is already pre-parsed for us. Right. We're going to put the parsing, like, you know, out of the equation. Right. And we'll see how it goes. So we need to be able to collect all of these things in there, all of the keys in a program, and turn them into a list of atoms. Right. So now we're going to have a variable list of atoms. So let me see. So as far as I know, in a program, you can take keys, right? So, and that literally gives you keys, and we can try to collect all of that stuff, right, into the atoms. Maybe, in fact, we could have something like atoms, which is a vector, because one of the atom that we're definitely going to have in here is the name of the module itself, which is a Bada, right? And then we can say that we're going to extend the atoms with the keys, right? So all of the keys that you're going to have in here, right? So we're going to push them into the atoms, and there you go, we got all of the keys. We might as well even print this entire stuff. So let's actually say atoms. The atoms that we managed to collect here are the atoms, and I'm going to try to just run the Bada. So we don't have a hash or anything like that. So let's actually do use std collections hash map. I think that's what you're doing here. There we go. So what do we have in here? So yeah, we have to put colon in here and push. So method push not found in the current scope. I think it's not called push. I think it's called insert in case of HashMap. There we go. So here are all of the atoms. That we got. Okay, that's pretty cool. So now, when we want to generate the atom chunk, we can just say, okay, so here are all of your atoms. So that's pretty cool. And so when we try to compile this entire thing, and then we're gonna go into this stuff, we can try to maybe take a look at the parser. So if I do beam read Bada beam, right? So this is Bada beam. I did a fucky wacky, oopsie doopsie, and here are all of the atoms, right? So we have Bada, world, hello. They are in a little bit of a weird place, right? To be fair, they are in a little bit of a weird place, but that's maybe fine. So that is maybe fine. I kind of feel like I want to have this system that automatically you can insert atoms and then you can query atom IDs. So that's one of the things I would love to have, right? So maybe it's going to be like a structure atoms, right? And one of the things you can do here is essentially fn get ID, right? Get ID, and you can get a mutable self and the name of the atom, and what it will give you the usize of that specific atom. Right, and as you can see, it actually mutates the atoms. And here we have an inner hash table, so HashMap, which probably stores the strings. So it probably needs to, you know, own them, right? And the result here is going to be that. So, and essentially, when you're trying to get a certain thing, right? So get the name, right? You're trying to get the name. If you found it. ID, you simply return it, but if you didn't find it, That's where it gets interesting. So we also probably need to get some sort of a counter, right? So counter use size. So, and essentially we increment counter by 1, right? We increment counter by 1. Then we do self inner, well, I mean, it's inside of the self. Insert name to string self counter. So we insert that stuff in here, and then we just return the counter as the ID. So as you can see, if it doesn't exist, it's going to be added in there, and so on and so forth, right? I think that's a pretty good idea. So, and we need a way to construct this entire thing. I think the default construction should be more than enough. So this is going to be something like default. There we go, default construction. So, and now I can do atoms default. So, and essentially, I could have actually implement extend for the atoms, right? So, but I mean, I can do something like this. So essentially key in program keys, right? And I can do, so I'm basically, and since it's sort of like lazy like that, since it's so lazy, maybe, nah, it would be better to actually pre-allocate all of them. Would be actually better to pre-allocate all of them. But maybe, what if we generate atom chunk the last? Because I feel like it doesn't matter in which order you put them, right? I think it doesn't matter. I'm pretty sure it doesn't matter. All right, so let me see. So I'm gonna actually back off a little bit, right? I'm gonna back off and try to generate the atoms last, because it would be kind of nice. It would be kind of nice if we passed the atoms like everywhere in all of these chunks as we generate the code and imports and exports, and atoms like lazily collect all of that stuff, and then at the end we generate the final list of atoms like that. You know what I'm talking about? That would have been cool, right? So that way we don't even have to think like how many atoms we're gonna have. We just generate as we go, referring to different atoms, and we just collect them, and then at the end we just generate the final list of atoms, and that will work. But I feel like, right, we need to confirm that this kind of stuff is going to generate a valid code at all, right? So let me see. So we have a code chunk, right? So let me remove that thing. So ID, this is a pointer. Can I just pattern match the pointer like so? Is that something I can do? Okay, so that seems to be working. So let's go into Erlang. Let's go into Erlang and try to read this entire thing. Okay, our parser managed to read that successfully. What about the disassembler? Disassembler didn't like something. Disassembler really didn't like something. Extract atom. Oh yeah, this is because we didn't put anything. So we need to have at least one atom in there. That makes sense. I do agree with that. Okay. So, and then if I try to disassemble that, okay, so disassembler is fine with the atom chunk being at the end, so it is totally fine with that. What about the actual virtual machine? Is virtual machine fine with this kind of shit? Virtual machine seems to be fine. So you can actually put the chunks in whatever order you want. That is pretty cool. That is pretty cool. I'm gonna try this idea of actually generating atoms the last, because new atoms may appear as we go, so to speak. New atoms may appear as we go. So when we're generating the code, we're gonna be accepting the program, right? HashMap. So it's str to use size, and this is basically the number that the function should return. Right, and we also should accept the atoms by a mutable reference, right? So that's basically what we have in here. That is basically what we have in here. So we are generating the chunks. The label count is going to be. This is actually rather interesting. How are we gonna approach this entire stuff? So we have 3. I suppose I can say we're gonna have 2 labels per program, right? 2 labels per program. So that means I can say len multiplied by 2. Right, we can do len multiplied by 2. Though we can just simply generate code in a separate chunk as well. Right, so we have chunk, then the code, and then the result. We can simply put this entire stuff into separate vector as well, if that makes any sense. If that makes any sense. So we can say let code, and it's also mutable, vector new, like so. And I'm gonna just quickly replace that. There's the code. And then in here, we can have label count and function count, right? Label count and function count, and we can put them up there and we can make them mutable. So that means as we generate the functions, we're going to be incrementing these labels. We're going to be incrementing these labels, right? So initially they are 0, but we're going to be incrementing them. Okay, that's cool. So I'm going to be iterating the name and result in program. So that's what we do. Name and result in program. So we generate a number, like a label. So to do that, we're going to do label count plus 1, and we're going to just use that label count. That makes sense, I think. I think that makes sense. So the next thing we do, we need to use atom for the module, right? So atoms get ID for the module Bada, right? So that's the module name. Then we do atoms get ID for the name of the function. Actually, yeah, so it's not string literal. What the fuck am I doing? Yeah, for the name of the function. So that's what we do. The arity of this function is going to be 0, right? So the arity is hard-coded. So since we keep repeating the Bada over and over again, it's going to use the same ID in there, right? It's going to use the same ID in here. So next we generate another label. I can actually copy-paste that specific chunk of code. I may actually factor out this code, right? Every time we generate a label, we increment the label and so on and so forth. So then we generate the move instruction and we move in the actual value in here, right? So this is the result we have to put in here, like so. Maybe we have to even dereference some of this stuff, like so. We put it into the X and then we return. And I suppose this instruction should be at the end of the code section, all right, that's cool. So, and what's funny is that we also need to increment the function count every time we encounter a new function. So it's a function count plus 1, right? So new function count, and all of that is going to be encoded down below in here. And then a chunk is going to be extended with the code, and then the result is going to be extended with the chunks. So we have like a 2-nested process of generating the code, right? So we have something like that. That is very interesting, actually. This is very interesting. Okay, so, and this is the code, and we have to provide the program and mutable atoms, right? Mutable atoms. Interestingly, we're not going to be doing imports, but we're going to be doing exports, right? So exports also will need program and the mutable atoms, right? Because we're going to be looking up the atom IDs and stuff like that. We don't really need to do anything with the string chunk, but the atom chunk must be accepting atoms, right? It must be accepting atoms. Okay, so I'm going to just try to compile the thing as it is, go through the compilation errors. Right, so extend chunk program. Program is actually not defined because I removed it. So what else do we have in here? Atoms is not in the scope. Let's define them. Let mute atoms. Atoms default. So this is going to be something like this. What else do we have in here? Label count. So as U32. It's actually as I32. And this one, so all of them as I32, as I32. label count as I32, and this one also as I32. Okay, so that worked. We can take a look at the parser of the beam, right, just to see what we got in here. Okay, in terms of atoms, we've got the atom Bada, but yeah, that makes sense actually. That makes sense actually. We got exports function name, Arity, label. That's a bizarre function, honestly. Like, why there's only one there? Oh, because we didn't export. Okay. We just generated some code, but we never exported anything in there, so that doesn't make any sense. But I wonder if the disassembler is going to understand this entire file. Yeah, it doesn't understand. Cannot disassemble instruction. Function, close function info 3. It didn't like the function info for some reason. Probably because we didn't put atoms anywhere correctly, so that makes sense. Okay. So can I just put mutable atoms in here, right? So we're gonna go into the atom chunk, and the atoms are gonna be, to be fair, atoms do not need to be mutable, right? We'll have to go internally, I think, right? So we're not gonna be modifying them, we're only gonna be looking at them. All right, so the atoms is inner length. And what we're iterating, we're actually iterating the inner thing, where we get the name. Yeah, this one is interesting because what we'll have to do, we'll have to turn it into a vector and sort them by their IDs. That is very interesting, actually. That is very interesting. Maybe instead of using HashMap, we should use a vector, at least for now. Right, we should probably use a vector. So, because it will make it easier to then sort like in order that is used by the indices and stuff like that, and that way you don't even need a counter. Right, so essentially what you can do, you can just iterate, then enumerate, right, enumerate, and then find. And what you're finding is the index, right? So index and the name, right? So there is a little bit, so there's a collision in here between that name and that name, so I have to call it slightly differently. So let's call it needle. So, and essentially what we're looking for is this thing, right? Maybe even without this kind of stuff, but yeah. Right, so this is going to be iterator, enumerate, find that thing, right? Find that thing. And if you found it, right? If you found it, we're going to return it. Otherwise, we're gonna do something else, right? So I'm just thinking how I'm gonna do it. This is the result, and then I need to match the result. All right, so match the result, and in here, what you have is an index and a name. So we don't really care about that name, but we can map the final thing, which takes an index and name and just maps it into index plus 1, because we are indexing from 1. Right, so that way you can just say, okay, ID result. Otherwise, you can just do self inner push, needle to string, and simply return self inner length. So that way, I think it's going to be easier. So let's go through the compilation errors. So atom, yeah, so inner len. What else do we have in here? So we're iterating inner, and surprisingly, that is literally it. So you have needle str. So can we just do it like that? No implementation for this string. That is most bizarre thing I've ever seen in my entire life. How can I compare this, mother flippers? Cannot move out. So I want to iterate. Index is not used in here. Boom. Look at that. Okay, so we're using vector instead of HashMap, so that should be fine. And now we're also generating atoms, and it just makes it a little bit easier. Right. So that's pretty cool. Atoms. And you don't even need the counter. We can even call this thing names, right? So these are the names of the atoms. And let's actually call them names. Names. Okay, that's pretty cool. All right. So let me see if whatever we generated even disassemblable. It is disassemblable. So the reason was it already freaking generated. Look at that. What the fuck? So hello is 69 and world is 420. So we generated 2 functions. So that means, holy shit, bruv. I can add more functions in here. I can say foo, which returns one hand is like something like this. Right, I can do that, and then in Erlang I can disassemble this entire thing, and now we have 3 functions, and foo returns exactly that. So it's already a mini programming language. This is already a mini programming language. So, right, this is so freaking cool. Right, so I just give it hash map of these functions, of these names and corresponding numbers, and it generates you an actual valid beam module with functions with the same names that return these numbers. It's a dumb language, I understand that, it's useless, but it's legit. So that means you can extend it, you can make it more powerful and stuff like that. That's what's important, right? You implement dumb shit but extendable, and then you extend it, and that's how you win, right? You go one step at a time. You go one step at a time. So, but none of that is actually loadable, right? Because we need to also export all of these things, right? We also need to export all of these things. So I'm thinking is that we need to take the program and immutable atoms and export all of this stuff. Right, so this is going to be program. Right, so it's a hash map str use size, and then atoms, atoms. And they're going to be mutable because getting an ID actually mutates this thing. All right, so export count is basically program len, right? It's a program len. Then we iterate through the program, right? So iter, and you have name and result, right? So it's a name and result. And here is an interesting thing. So you're supposed to provide a function name. You're supposed to provide a function name. So it's atoms get ID, name, like this. Then arity is 0 and label. Okay, go. Okay, go. Label is 2. Okay. Where can we get that shit though? Where can we get that shit though? I don't really know. So we need to, when we manage to compile each individual function, we need to save its label. Right, so code chunk. Look. So we have this label which starts at here. And then we have the second label in here. We need to somehow save that label. We need to somehow save that label as we compiled. All right, so we may have something like labels, hash map labels, and it's going to be str, and maybe it's going to be u32 or something, and it's going to be something like this. So it's a very dumb solution, but I'll think how to make it better. Labels insert. And the name, we're gonna start maybe by string name. Huh. So we already kind of, yeah, so let's actually use string name and label count. Right, so these are the labels. These are the labels. Okay, so program expert usize as u32. Atoms is not an iterator. So what do you say? As u32 2b bytes. So here is the name. What else do we have? Code chunk. You need labels. Okay. Let's define labels. So labels is also that. But we actually said it's going to be u32 for whatever reason. Sure. So as we compile this entire thing, we collect all of the labels, so that's fine. Oh, and if you want to do labels, you have to do lifetime. So, okay, that's going to be painful. That's going to be painful. So instead of doing that, maybe we should collect the atom IDs, right? So get ID. Right, so get ID, so it returns usize. Yeah, so this is going to be usize. Let's not do that. I don't want to go into this kind of shit. All right, so name ID, and we can put it name ID like so. Right, so this is a name ID, and this we're gonna have a name ID. All right, so that will make it a little bit easier to do this entire shit. And label is usize. Alrighty, so when we export, and here's an interesting thing, we don't need the program name, we can just have labels. Yo, that makes it okay. So this is a name ID and this is a label. The fuck, bruv? Bruv, what the fuck? It's just naturally writing itself. What the hell? Right, so might as well even make name ID u32. So I never have to convert it. So the Arity is 0, we know that for a fact, and then I just use the label. What the hell? That is such a cool idea. I just like naturally discovered, like, yeah, you compile code from list of names and numbers into a list of name IDs, atom IDs, and the labels where it is located. So yeah, actually program and labels are the same entities. This is a raw program and this is compiled version. Holy shit! And this is so freaking cool. So this is the same thing. This is uncompiled program and this is program after compilation. This is mind-blowing. It's funny how I just discovered that by just writing the code and messing around. Oh my god, this makes so much fucking sense, right? Code chunk takes the program and compiles it into list of labels. What is going on? Like, what? It's like an enlightenment for like wait a second, it's the same thing. Wow. Holy shit. Anyway, I'm sorry. It's just like it's kind of difficult to convey what is going on in my head right now, but I mean, I'm trying. So, and expert count is going to be just the labels then, right? So that makes sense. And just like this is the labels, right? So it's the name ID. Yeah. So here is that. But when I do code chunk, right, this has to. You can't see scheiße in this mist, but yeah, that's what I do in here. So mismatched. So this is a name ID. And name ID is defined in here as, well, I mean, when we assigning that stuff in here, I hope I'm not making any mistakes, so actually. So export chunk, and this is the labels. Right, so look, compiling the code, program into labels, right? So the output is sort of, the result is the labels. And then to export those chunks, I'm providing the labels, but I don't provide the original program. I don't provide the original program to export it. I'm exporting the compiled result of the program. And the compiled result is just like the atom of the name and the label where the function starts. And I go. So surprisingly, because of that, you don't even need to provide the atoms. What the fuck? Oh my god. Holy shit. Okay. Input is the program. The output is all of the atoms and all of the labels of the functions. and those outputs, labels go into the experts, and atoms goes into the atom chunk. And you can even see that through the mutability. The compiled program is immutable. The two outputs out of the program are mutable because this is the outputs. And the same outputs from the code compilation are inputs for the exporting. And so let me see. Hopefully this entire shit will work. So let me try to maybe just disassemble that. Okay, so everything seems to be working. Here are all of the atoms. I'm quite surprised. Okay, so this is not the atoms, this is the exported function, so I'm being a little bit silly right now. So if I read this entire thing, here are all of the functions we exported. Here are all of the... So, and this is a little bit bizarre, because the module... Like, I don't remember, I think we had coded the module name to be 0 in some places. I have a feeling that we did. And that may bite us in the ass in the future. But anyway, YOLO. So let's just try to purge the code and just load it. Okay, so module name object is full. Yeah, that's exactly what I expected. So where did we use that stuff? I forgot to update. So I need to go through all of the chunks then, right? So chunk name, function count. Did we... Right, so here when I do function and for, we just do that. So that seems to be fine. I don't think code is an offender anywhere in here. Import chunks, they're empty, they don't refer to the modules. That's fine. Export chunks, maybe, by the way. Export chunks may be referring to some modules. So you have a function name, you have that, you have a label. So an atom chunks, I don't think they... Okay, I have a strange feeling that the module name is the first atom. I have this kind of feeling. So, and we refer to this kind of stuff. So atoms... Yeah. So since we refer to the atoms like name first and only then to Bada, Bada doesn't end up to be the first name in the atom list, unfortunately. Okay, so let's just try to do it like that. Let's try to disassemble. Maybe look at like that. There we go. So now Bada is the first, right? And I feel like, I don't have any information to confirm that, but I feel like the first atom has to be the name of the module as well. Right, so we have the module and then the rest of the functions in here. Okay, so then we try to take a look at the disassemble, right, and then let's purge and reload. Okay, so... the amount of labels is incorrect, so I feel like the label count has to be sort of like +1. Let's do, after we finished all of that, let's just do label count +1, just in case. I still can't not understand how the label count works and all of that jizz, but that works now. So Erlang get module info. By the way, isn't Erlang automatically imported? So I should probably be able to do something like this. Nah, it's not. There we go. So we have experts, we have foo, hello, and world. So that means I should be able to do Bada foo. It's that, hello, world. So if I want to add a new function in here, so what I have to do, I have to just do bar and just put some stuff in here. Right, I'm going to recompile this entire thing. Right, and then I'm gonna reload the module. Right, I'm gonna reload the module. And now that module, just a second, I'm gonna take a look at that. The module info contains bar. Like a legit beam module contains bar, and I can do in Erlang Bada bar, and it contains that number that I put in there. So I have the compiler from the HashMap, to beam module, this Bada beam module. So the next step is to actually do something like this, compile this kind of file. This is going to be the next step. Should we do that? Bada beam, bada boom. So what we need to do, so as far as I know, in FS, there is read to string. So test Bada, right? Expect. So let's actually do something like input path. Right, input path. So this is going to be that. Content. So we got content, and we can maybe do something like content length is equal to content len. So boom, what do we have in here? Content len 22. Content len 22. Okay, so we can maybe even print that content. Yeah, so that's the well, I mean, it would be nice to get rid of this entire thing, but so yeah, we got that. Can we split content into lines? Is that something we can do? So essentially, I can say line. We can. So we just split this file into lines. So we're also gonna have like empty lines. Which is not particularly pleasant, so this is something that I want to do like that. Line len greater than 0, only then we're going to consider those lines. So we filter out those things, right? We filter out those things. So within that line, we probably want to split this entire thing by sort of equals, right? So, and we're going to have some sort of chunks. Right, and the question is, what are those chunks? How do they look like? How do we process them even further? How do we process these chunks even further? What the fuck is this shit? Can I just collect that into a vector? Right, so is that something I can do? Okay, so we'll get those things. So, and essentially, what if I have like something like this? Right, so we have really wacky format, So how does it look like? Okay, so we've got these kind of things. So we can essentially take chunks. We can even maybe match this stuff. If let key value chunks, only then we're gonna care about them. Right, only then we're gonna care about them. Right. So then in here I can do key. Do we have something like trim and value trim? Is that something that we have? So then later I can do key equal key, and then value equal to that. Can we do this kind of stuff? Okay, so what you don't consider slicing here, pattern matching. I see. Alrighty. So we can also do, so what do we use? We use parse use size, something like this. And I'm gonna simply unwrap for now, right? So unwrap for now, and what do we have in here? We have this kind of stuff. So the only thing that is left in here is basically program insert key value. But we have to be a bit careful in here because maybe not. So we are referring to string, and it refers to the content, and content lives as long as the program. So I think lifetimes are gonna be fine. So that should just compile now. There we go. So now here's an interesting part. I'm gonna do the following thing: 1, 2, 3, 4. Here is the file. I can even align this file. I run Bada. That Bada takes this file and transforms it into the module Bada beam, right? So we take that module and we load up that module in Erlang, right? And let's take a look at the module info. 1, 2, 3, 4. Bada 1, 2, 3, 4. We wrote a legit programming language. Oh, well, I mean, it's not Turing complete or anything, right? So we can even test something like your mom, right? Doesn't exist. Go back to test Bada. Your mom, 69. Recompiling the whole thing. Reloading the whole code. Bada, your mom, it's there. Easy peasy. Squeezy. So there's the last thing that is left, right? It's kind of funny how you just like build on top of like, I'm actually started inside out. I started with the code generation, right? Then with the compilation, and then with parsing. How people usually develop compilers, they develop Elixir, Parser, compiler, code generation. They usually go from the front end to the back end. Has anyone tried to develop compiler started from the back end to the front end? I think it's kind of more fun, to be fair, right? So, right, because since you're starting from the back end, you get a final working result faster, right? So you started from the backend, right? So you start with assembly. You already have a thing that is running, you already have a thing that is working. And then you build up on top of that, going back to the front. That's a very interesting technique of developing compilers, honestly, and interpreters and stuff like that. Start from the backend, from something that is already runnable, from something that is already working, and work your way towards the front end. Start from the both sides and meet in the middle. I don't know, maybe. So the only thing we don't really do in here is that we have hard-coded input path and output path, right? So that kind of sucks in my opinion, to be fair. So that doesn't feel like a legit compiler, if you know what I mean. Right, doesn't feel like a legit compiler. So what would feel like a legit compiler is to actually accepting the input path and generating output path based on that. That would have been actually kind of cool, I think. So let's actually try to do that. So this is going to be the environment, and right, so args, we take the args, so mutable args. So the first thing is probably going to be program, so we can do expect program, and we can do the following thing: some input path args next. And we can just return this thing, otherwise we can generate an error, println error, no input is provided. And there we go, we've got an input path. There we go, we don't need this shit anymore. The output path, how do we even like do that? So I do quite remember, so there was a path thingy. If I construct a path out of that, canonize extension. So we can extract extension out of this thing, but can you do that with extension with file name? So what I want to do, I want to strip off the file extension and then append like a different one. So you have a path with extend. Oh, okay. So path with extension txt. Okay, so let's give it a try. path new input path with extension beam. Do I have to put dot in here? I don't have to put dot in here. I think that's fine. Okay, let's go to the compilation errors and see how it's gonna go. Okay, so path is a part of the std path. std path. What else? Expect no method. This one has to be next. Else, yeah. So here, what we have to do, we have to kind of return. Let's do exit one. Std process exit. So this is basically crash. Okay. Expected, but this is a string. Expected str. Well, I mean, nah, that's fine. I mean, we can always do some stupid shit like match. It's not really that important, honestly. If error println could not write file an output path. Remember that you can't really easily display the path buffer, so there is a special sort of like a display thing, right? Yeah, so there's a special method to display this kind of stuff and everything, right? Because they may contain something that is not UTF-8 or whatnot on some operating systems, so you have to be kind of careful with this kind of stuff. So output path is going to be this, and then we're gonna basically do std process process. I said exit one. So this one is unused. That's fine. Error is unused. It should be used. Okay, so borrow out of moved. Goddamn Rust! I swear to God. Goddamn Rust. All right, so let me actually do something like this. It's just like sometimes it just forces you to spend some shit, like time on unimportant shit, and just compile my program already. Just compile my program already, please. Rust do be like that. Not sometimes, but every single freaking time. Okay, what we need to do, chat, what we need to do, we need to test this kind of stuff properly, maybe in a separate folder, right? So I actually want to open up a separate terminal. So it's going to be sodium Bada. Right, so let's do test. And I'm going to go into the test, and I'm going to copy the binary in here. So we have Bada. Can you see shit, by the way? I think you can't see shit. What if I do something like export ps1? Right, it's ps1 and then just that. So look at that. I think that's better for, you know, for the demo and stuff like that, right? So let's go and open bada.bada, right? Bada.bada, and we're gonna say 1 is 1, nice is 69. Right, we have two things in here, and I do Bada, generated bada beam, bada boom. Right, so you can clearly see that here is bada, and here's the bada beam. Here's bada beam. The next thing I do ERL, and then I do code load file Bada. That's the result of today's stream. So what you can do now with Bada, you can take the file, right? So Bada with sort of like this list, name number, and you can compile it into the beam file, an actual bytecode of Erlang, where each name is an Erlang function that returns this number. this is a thing that is extendable. So now, instead of number, you can accept a sequence of actions, and you compile this sequence of actions to some instructions in Erlang, and you get a programming language that compiles to Erlang bytecode. I think I now know why things like Elixir and Gleam are a thing, because Erlang VM is a very easy compilation target. It's a very easy compilation target. Like, you can just compile to it. It's a relatively straightforward virtual machine. Even being half as documented, you can still figure it out. Gleam compiles to Erlang code and not to the Beam code. Pathetic. Pathetic. Oh my god. How am I supposed to even take it seriously now? I'm disappointed. I'm disappointed. Anyways, so we have like 5 minutes, so I should probably create the repo for all of that. I should probably create a repo for all of that. I already have a repo. I mean, yeah, so I can compile it to the same repo, essentially. So I can remove that. Beam. I can compile this stuff, right? So print info for the code chunk, right? For the code chunk. All right, and we're gonna go ahead and just implement Bada compiler in Rust. Boom, and I'm gonna push that right into the repo. So and I have Bada, right? I have Bada, and it's private repo. So now I need to make it public. So let me see. Oh yeah, like making it public is such a pain in the ass. So this is a danger zone. This is a danger zone. Look how many clicks they add so you can make it public. And now you have to... This is fucking genius. Like, this is in case some dumbass intern doesn't accidentally publish like business important code, like so many clicks and stuff like that. It's fucking insane. I really love it. You can feel the intent. You can feel the UX, and just like, are you fucking sure? Are you fucking sure? Almost had a heart attack. Whew, okay, so it's public now. Right. So you can find this thing in here, and for people who's watching on YouTube, of course, it is going to be in here. So this is already a different day, right? I forgot to create a section for the next stream. All right. So I guess that's it for today. Thanks everyone who's watching right now. I really appreciate that. Have a good one, and I see you all on the next recreation programming session with Mr. Zozin, as usual. So yeah, thank you. Thank you for watching. Love you all.